starting with the Polygon tool. Before I begin sketching, notice the Property Manager allows me to specify the number of sides. I'll specify 8 for this example and use the inscribed circle option. While the polygon is selected, I can change the setting to circumscribed circle and you can see the result. The construction circle gives you a convenient method of dimensioning the polygon using a diameter dimension. Notice the polygon is free to rotate. You can add relations such as horizontal or vertical to further define the sketch. Often during the course of modeling complex shapes, you find yourself using the spline tool in your sketches. While there's nothing wrong with that, splines can be difficult to define and control. If you can use other more easily controlled tools such as ellipses and parabolas, the results of features like sweeps and lofts can be much more predictable. Let's take a look at some of these tools, starting with the ellipse. Sketching an ellipse is a two-step process. You click and drag one axis of the ellipse, then click and drag the second axis. Once again, you click and drag once, then a second time to complete the ellipse. Notice that although this point appears to be lined up with the center, there's no automatic relation added, so the ellipse is free to spin. There are several ways of keeping this from happening. One is to add a horizontal relation between these 2 points. This is a widely used method, and it certainly keeps the ellipse from spinning. But I would suggest using a different method where it's easier to tell that a relation has been added. For instance, if I sketch a construction line from the center to this point, a horizontal relation is added. This keeps the ellipse from spinning, and it's obvious to anyone that might edit this sketch in the future that a relation exists. Another nice thing about using construction lines is that they provide a convenient way of dimensioning the ellipse.
There's another tool related to creating an ellipse that I'd like to make you aware of. It's called the partial ellipse. Using this tool will help you avoid creating a full ellipse and then later having to trim it if you only want to use a portion of the overall shape.
Sketching a partial ellipse starts with clicking to define its center, clicking again to define one of the axes, and clicking a third time to begin sketching the shape itself. Once you start sketching the shape, you just drag your pointer and click again to complete the partial ellipse. If this seems complicated, it is. In fact, the partial ellipse and the parabola, which we'll take a look at next, are the most difficult sketch tools to get used to. Let's go over the partial ellipse one more time. Click to mark the center, click to establish one of the axes, and click again to start the ellipse. Drag out the pointer to draw the shape you want to end up with. Defining the partial ellipse can be accomplished just like the regular ellipse. Use a center line to keep the partial ellipse from spinning, and a couple of dimensions to control the size. Also, if you're like most people, you'll try to delete these points. You can't. They're the defining points for the ellipse. They mark the location where the minor and major axes would be if this were a complete ellipse. Deleting these would be like deleting the center point of a circle. Another helpful sketch tool in creating complex shapes is the parabola. I mentioned earlier that this was a difficult tool to use. Maybe difficult's not the best way to describe it. It just involves several steps, and for some people, that makes it difficult to control. Here's how it works. You begin by clicking to establish the center, or more accurately, the focus of the parabola. Next, you click to define the vertex, and then you click to begin the parabola. Now you move your pointer to draw out the shape and click once again to complete it. One more time. First, you click to mark the focus, then click again to mark the vertex. Next, you click to mark the beginning of the parabola, drag your pointer to draw out the shape, and click one more time to finish. Defining a parabola really depends on what you're trying to accomplish. One thing I would recommend is adding a center line from the vertex to the focus. This gives you a way of establishing a direction for the parabola, such as making the line vertical, and it provides a convenient place to add a dimension. This dimension will control how wide or narrow the parabola opens. Making use of the parabola even more intimidating to some users is a bug that exists as of SolidWorks 2005 Service Pack 0.0, As you make changes to the dimensions that control parabolas, SolidWorks has the bad habit of reporting invalid or unsolvable solutions. Your sketch will become yellow or red, indicating there are errors. However, if you accept the dimension, the error will go away.
A conic is a figure formed by the intersection of a cone and a plane. The Conic tool in SolidWorks lets you define a conic curve in a 2D sketch based on endpoints and a row value. Just launch the Sketch tool from the Tools, Sketch Entities dropdown, and then there are 4 clicks required to create the conic curve. The first endpoint, the second endpoint, then the third click defines the top vertex, and the fourth click sets the row value of the curve. Again, the clicks are endpoint, endpoint, vertex, and row. You can also set these values manually in the Property Manager. Conic curves can reference existing sketch or model geometry, or they can be standalone entities. The most common use of a conic is used to blend 2 other curves together. There are a few ways to define the sketch, but in my opinion, one of the easiest and most useful ways to define the conic is to attach both endpoints to other curves. Then add tangent relations to both the endpoints. And the dimension to define the row value. Making the vertex tangent to both inference lines of the 2 curves is a good practice as well. But again, it depends on the curve that you're trying to create. I'd like to go into the row value a bit more. Row is a number between 0 and 1 that describes the relative angle of the plane intersecting the cone and a conic. High rows make the conic sharp, while low rows make the conic round. Conics are always planar and simulate the look of a C2 or G2 blend, or in other words, a curvature continuous blend. And since it's second order mathematically, there won't be any inflection points. The spline tool might be the most flexible of all the sketch tools. Instead of trying to explain it up front, let's look at an example. I'll launch the spline tool from the sketch toolbar. I'll click once to start the spline, and click again to add additional spline points. You need at least 2 points to complete a spline, but you can add as many as you need. You can leave the spline as an open contour, or you can close it back at the original point. Again, it's very flexible. To finish the spline, either double-click when placing the last point, or press the Escape key on your keyboard. You can click and drag the points on the spline to reposition them, and add dimensions and sketch relations between the points to further define their position. However, even if you fully define the locations of all of the spline points, you might have noticed the spline still appears in blue, meaning something is still underdefined. Let's take a look. Notice if I select a single spline point, 2 gray arrows appear. These drag handles control the curvature of the spine. I can adjust the angle of the arrows by clicking and dragging the diamond shape, and the magnitude by clicking and dragging the endpoint of the arrows. I can also add dimensions or relations to the drag handles. Be careful when doing this, because if you exaggerate the angle or magnitude too much, you'll get an error and the geometry will fail. In order to fully define a spline, you must define both the locations of the spline points and the magnitude and dimension of the drag handles. So keep that in mind when using splines to create geometry. The more spline points you add, the more work you'll have to do to fully define it. That being said, I generally tend to only create 3 or 4 point splines for serious projects. That way I can fully define and dimension the spline geometry in order to create accurate drawings for manufacturing. However, if you're modeling something for fun and just want to get something close to the general shape of the design, then the spline can be a quick tool to use to create a complex sketch shape, as long as you don't care about fully defining the sketch. There are several reasons you might need to split sketch entities.
For instance, if I want to remove a section of this circle, I would have to either delete it entirely or recreate it as an arc, or I'd have to trim it. The problem with trimming is that I would need to create geometry, such as construction lines, to establish the trimming boundaries. Another alternative is to use the Split Entities tool. You can access this tool from the Tools drop-down menu in the Sketch Tools section. You can also access it more conveniently by clicking on any sketch entity and selecting it from the pop-up menu.
Once the Split Entities tool is active, just click to split the sketch segment.
You can create as many splits as you need. Now I can take this section and delete it, or convert it into construction geometry without affecting the rest of the circle. We'll see an important application of the Split Entities tool later when we look at creating lofts. As you probably already noticed, when you create models in SolidWorks, you spend quite a bit of time creating sketches. One technique you can use to save time is copy and paste. You can select a sketch file like this one here from the Feature Manager tree, click Edit, Copy, or Control-C, and then pick the face or plane where you want to paste the sketch. Click Edit, Paste, or Control-V, and that's all there is to it. Now, wouldn't it be nice if when you made a change to the original sketch, the one you copied also changed? You can accomplish this using the Derived Sketch command. You can find this command on the Insert drop-down menu. In order for it to be active, you have to pre-select two things: the sketch you want to copy and the face or plane you want to copy it onto. In this case, I'll select the original sketch used for the cut and this face. Now I can use the Derived Sketch command. Notice the resulting sketch does not have dimensions on it. This is because it's completely controlled by the original sketch. All you can do is add dimensions or relations to position it however you wish. Watch what happens when I go back to the original sketch and make a change to a dimension. When I rebuild the model, the copied sketch remains unchanged while the derived sketch updates. If you ever want to break a derived sketch so it's not related to the original, just right-click on it and select Underive.
If you are ever having problems working with overdefined geometry in a sketch, SolidWorks has a tool that helps you automatically resolve any conflicts. It's called the Sketch Expert, and it works with both 2D and 3D sketches. Let's take a look by overdefining the sketch I have here. I'll input a conflicting dimension and leave the dimension driving so that it overdefines the sketch. To activate the Sketch Expert, simply click on the error message that appears in the bottom of the status bar. This brings up the Sketch Expert Property Manager. The Sketch Expert gives you two options for fixing the sketch. You can fix it automatically by clicking the Diagnose button, or you can use the Manual Repair mode to see all relations with errors and fix it yourself. Let's look at the Automatic option first. I'll start by showing you what happens when you press the Diagnose button. When I do, the Sketch Expert analyzes the sketch to find solutions to the sketch error. You can see the results box appear in the Property Manager, and you can use the arrows to toggle through the different possible solutions. Notice in the graphics area, the dimension or relation to be deleted is displayed with a strike through, and an image of our original sketch geometry is still displayed. Once you've found the solution that works best for your design, just click Accept, and the Sketch Expert makes the change for you. A message window shows that the sketch can now find a valid solution, and I can click the green check to exit the Sketch Expert. But before I do, notice this checkbox here. I can activate this checkbox to automatically launch the Sketch Expert every time I get an error in a sketch. I'll check it and exit the Sketch Expert. Next, let's take a look at the Manual option. I'll add another dimension, and again leave it driving to overdefine the sketch. Notice Sketch Expert launches automatically because of the checkbox we just activated. This time I'll click Manual Repair. When I do, I see a list of all of the relations and dimensions that have conflicts. As I click through each one, you can see it highlight in the graphics area. And I can click the Suppressed button to preview how moving it affects the sketch. If you don't like the results, just press Undo to return to the full list. Once you've found the dimension or relation you like to remove, you can press the Delete button. I don't use the Delete All button very often, but if you have a sketch that's completely unsolvable and you can't tell what to fix, you can use it to remove every one of the conflicting dimensions and relations, so you can start from scratch. Once everything is fixed the way you want it, just click the green check again to exit the Sketch Expert. SolidWorks lets you insert an image file into a sketch that you can use as an underlay as you create sketch geometry. This can be useful if you're trying to trace the outline of a shape or to model something based on a picture you may have taken of it. I'll begin by creating a new sketch on the front plane. One thing I like to do before inserting the sketch picture is to create and dimension construction geometry. You don't need to do this step in order to insert a sketch picture, but I really recommend doing so as it makes it much easier to locate and size the image later on when you insert it. I'll create a horizontal construction line from the origin. Next, I'll add a dimension. I'll add a 24-inch dimension to the horizontal construction line. Now I can launch the Sketch Picture tool from the Tools, Sketch Tools drop-down menu. SolidWorks let you use many different types of images for a sketch picture, like a bitmap, a GIF, a JPEG, TIFF, PNG file, or a WMF or PSD. When you find the image, click Open, and the Sketch Picture Property Manager appears. The Sketch Picture Property Manager is pretty straightforward. You can use the spin boxes, or you can drag the sketch picture in the graphics area. I pretty much always use 0, 0 when starting a new image. That way I can be sure the image and my construction geometry is aligned properly. The next field lets you rotate the picture. I'll leave the angle set to 0. Finally, I can adjust the image size. Again, I could do this by clicking and dragging the image in the graphics area, but I'll just enter 24 for the width. Notice the height updates automatically because I have the Lock Aspect Ratio checkbox selected. I like to keep this checkbox active because changing the aspect ratio will distort the image from the original. But if you need it to fit a certain size exactly, you can clear the checkbox and adjust the values accordingly. These two buttons here let you flip the image vertically or horizontally if it imported in the wrong orientation. Finally, you have transparency options at the bottom. You can have no transparency. Use the transparency from the image file, for instance a PSD with a transport background. Set a transparency value for the full image by using the slider under the full image option. Or you can create a user-defined transparency. For user-defined, you can use the eyedropper to select a specific color in the image to make transparent, and then use the sliders to adjust the tolerance of the color and the transparency amount. This is useful if you have an image with a white background and want to make it transparent. I'll use the transparency from File for this example and click the green check to insert the picture. If you need to edit the sketch picture, just double-click it to bring the Property Manager back up. You can select it and press the Delete key to delete it if you ever need to, too. If you've inserted a sketch picture into a part, you can use Auto Trace to trace the image. Auto Trace is fast, but it can be tricky to get good results consistently depending on the quality of your image, how you set it up, and other factors. If you're using Auto Trace, there are a few tips on the image that will get you better results. You should use a high-resolution image if possible, with a minimum of 300 dots per inch. Line art should ideally be pen on paper, with precise contours, and as high of a contrast as possible. You also want the colors in the image to be as uniform as possible, meaning minimal shading of gradients. Black and white or other high-contrast images work the best. Again, it might take you some practice to use Auto Trace effectively on a consistent basis, but once you do, it's much quicker than tracing an image by hand. I'll begin by activating the Auto Trace add-in by going to Add-ins and checking the checkbox next to Auto Trace. With the Auto Trace add-in active, I'll double-click the sketch picture to bring up its property manager. Notice it now has a forward arrow at the top of the property manager. I'll click the arrow to switch from the sketch picture properties to the auto trace properties. There are a lot of trace tools, and I definitely recommend playing around to figure out the method you like best. First, choose a selection tool and create a border around the part of the image you're trying to trace. If you've used Photoshop before, you're probably familiar with these tools, such as the lasso and the rectangular marquee. Once you've selected the image, click Begin Trace to have Auto Trace trace the image. You'll see a preview of the traced image appear in blue, and you can use the adjustment sliders below to adjust the tolerances. You might have to spend some time tweaking the sliders to get it perfect, but it's quicker than tracing it yourself. Once the sketch geometry looks correct, click Apply and it's added to the sketch. Notice the Property Manager stays open, and you can repeat the process selecting a different area of the image to trace. Once you've gotten everything converted to sketch geometry, just click the green check, and you're done.
Creating 3D sketches in SolidWorks can take a bit of getting used to, but it's a skill that can be a big time saver if you have to design things like tubing, piping, or weldments. To begin a 3D sketch, you can use the 3D sketch icon from the sketch toolbar, or you can use the 3D sketch command from the Insert drop-down menu. At first glance, not very much is different between the regular 2D sketch environment and the 3D sketch environment we see here. If you look closely, you'll notice a 3D sketch is listed in the Feature Manager tree, and the status bar reports that you're in fact editing a 3D sketch. Other than these indicators, the majority of the same sketch tools are available, including lines, arcs, rectangles, and splines. There's also a sketch tool available only in 3D sketches called Plane. We'll talk more about that in a moment. First, let's take a look at the basics of 3D sketching. I'll begin by selecting the Line tool from the Sketch toolbar. Notice that red arrows show up at the origin matching the X and Y directions of the reference triad here in the corner. Also, next to the pointer, you see the XY indicator. This feedback tells me that if I start sketching a line, it will lie in the XY plane, which has the same orientation as the plane we call the front plane. Before starting the sketch, I'll press the Tab key on my keyboard. Watch what happens as I do this. The red arrows move into different orientations, and the indicator next to the pointer changes. You'll see the XY, YZ, and ZX orientations become active. This ability to change the active orientation of your sketch is what makes 3D sketching powerful. Instead of creating several 2D sketches and the reference planes that go along with them, you can use 3D sketches to accomplish 3D geometry in a single step. Here's a basic example. I want to begin in the XY direction, so if necessary, press the Tab key to be sure the XY direction is active. Next, I'll click on the origin to begin sketching a line. This line will lie along the Y direction. If I were in a 2D sketch, this would be the vertical direction. Next, I'll continue with the line segment in the X direction. So far, these segments lie in the XY orientation, and they're essentially a 2D sketch. Let's break out of the 2D plane by pressing the Tab key, making the YZ orientation active. Now, I'll sketch a segment in the Z direction. Using the Tab key again, let's make the XY orientation active again, and sketch a segment in the Y direction. To complete this simple example, let's add a segment in the X direction and turn off the Line tool. You can see as I rotate the sketch that I've got a 3D structure that could not have been created using a 2D sketch. In fact, to create this using 2D sketches, it would have been necessary to create two reference planes. Although what I've shown you so far may seem very basic, I do recommend you try using the Line tool along with the Tab key to create some basic 3D structures like this one. Many users struggle to understand the important role of the Tab key and become frustrated when trying to use 3D sketches. In the next lesson, we'll create a slightly more complex 3D structure along with relations and dimensions. In this lesson, we'll create a 3D structure similar to one that would be created for the design of piping or bent tubing. We'll create the necessary geometry using a 3D sketch, and we'll add the necessary dimensions and sketch relations to fully define the structure. To begin, let's create a new 3D sketch using the 3D sketch icon from the sketch toolbar. I'll use the line tool and create a segment beginning at the origin and running along the X direction. When using 3D sketches, I recommend you pay attention to the length feedback next to your pointer. In this case, I want this segment to be 12 inches long. I'll use the feedback to make sure I'm close to this value. Not exactly 12 inches, but close. This will make it much easier to define the sketch later using dimensions and geometric relations. When the segment is completed, you can see it in Properties in the Property Manager. Next, I'll sketch a segment in the Y direction about 8 inches long. The next segment will be in the Z direction, so I'll press the Tab key to make the YZ orientation active. You'll see the YZ feedback next to your pointer, and if you pass it, keep pressing Tab until it reappears. The segment will be approximately 6 inches in the Z direction. Next, we're going in the X direction, so I'll press Tab to activate the ZX orientation and sketch a segment approximately 6 inches long. Next, I'll create a segment in the Z direction about 5 inches long, followed by a 5-inch segment in the X direction. Now, I'll create a small segment in the Z direction and then switch to the XY orientation to create a line in the Y direction. To finish the structure, I'll sketch a segment in the X direction about 12 inches long. Now that the shape of the structure is finished, let's add some definition to it. As you can see right now, it's mostly blue, meaning it is underdefined. I'll begin by adding some geometric relations, starting with the 2 long segments in the X direction. I would like for these to be collinear. I also want the 2 vertical segments to be equal. Instead of the equal relation, I can accomplish the same relation by selecting the upper endpoints of the segments and choosing the along X relation.
Adding dimensions in 3D sketches is a little bit different than in a 2D sketch. I'll launch the Dimension tool and select these 2 points. When I do, SolidWorks displays the vector magnitude or point-to-point length between the points. If I press the Tab key, you can see I have the ability to add dimensions in a single direction. The cursor feedback lets me know which direction the dimension is being applied in. I can toggle using the Tab key and dimension along the X, Y, or Z axis, along with the point-to-point or overall length. This makes adding dimensions to 3D sketches easy and intuitive. Also, notice that the dimension text is oriented on the screen with respect to the plane that it's being added in. This not only helps keep the graphics area looking clean, but also makes it easy to identify exactly which sketch entity or direction a dimension is controlling when you're making edits. I'll quickly delete this dimension and instead add a 1-inch dimension to the smallest segment of the sketch.
Next, I'll define the gap between the 2 vertical segments, and I'll set it to 2 inches. Both horizontal segments at the bottom will be 12 inches. And the 2 longer segments in the top portion will be 6 inches. As you progress with defining a 3D sketch, remember you can always stop and drag the remaining blue geometry to find out what remains underdefined. I recommend you do this more in 3D sketches than in 2D sketches. The reason is that in 3D sketches, it's possible to add many relations that are redundant or unnecessary. Rather than adding relation after relation, check to see what else you really need to define. In this case, you can see I can drag the blue geometry up and down, so I need to put in the 8-inch vertical dimension. This makes the sketch fully defined. To complete this example, I'll add some fillets to break the sharp corners. And finally, I'll create a circular profile on a new 2D sketch to sweep along the 3D path. The diameter I'll use is 0.4 inches. In addition to using the default planes or creating your own reference planes for use in a 3D sketch, there's a special type of plane you can create on the fly while in a 3D sketch. This is not the same as a reference plane. The main difference is that reference planes are fixed in space once you define them. Planes in 3D sketches are not. They can be defined using dimensions and relations just like any other sketch entity. Let's take a look at an example. Here I have a 3D sketch with 3 line segments already created. These are aligned with the X, Y, and Z axes and are here primarily to help us with visualization in 3D space. To create a 3D sketch plane, you can use the plane icon from the Sketch toolbar or from the Tools Sketch Entities drop-down menu. Notice the difference between this and a reference plane, which is found in the Insert Reference Geometry drop-down menu. The Plane Property Manager will appear showing selection windows for first, second, and third references. In a moment, we'll see how these references can help you define planes as you create them. In this case, I'll simply click OK and a plane is inserted into the sketch. Notice the Sketch Property Manager lists the plane with a minus sign in front. This minus sign indicates the plane is underdefined. If this plane were any other sketch entity, it would be shown in blue, indicating that no relations or dimensions had been added. Because the plane is completely underdefined, I can use the plane manipulators, these yellow dots, to move and rotate the plane in 3D space. Just like other sketch entities such as lines and arcs, I can use geometric relations and dimensions to define the location of the plane. For instance, I can show the front reference plane and make the 3D sketch plane parallel to the front plane. Next, I can put in a dimension. Be careful when using dimensions that you're accomplishing what you want. For instance, if I put in a dimension from this point to the plane, what I've done is tie one undefined entity, the point, to another undefined entity, the plane. Now when I move one, the other will move along with it. This is much different than putting in a dimension from the same point to the origin, or the front reference plane. At this point, let me add another plane, this time using references to position it right from the beginning. I'll click the plane icon on the Sketch toolbar, and for the first reference, I'll select the vertical line. When the line's selected, the applicable geometric relations will appear below the selection window. In this case, coincident, perpendicular, and parallel are available. I'll select coincident. For the second reference, I'll select the right reference plane from the Feature Manager tree and specify a 45-degree angle. You have the option to specify a third reference, but in this case, I'll click OK to complete the new plane. One of the main reasons you'll want to use planes in 3D sketches is so you can sketch on them. In order to sketch on one of these planes, you first have to activate it. To activate a plane in a 3D sketch, double-click on it. You'll know the plane is active because a yellow frame will appear around it along with the yellow control points. While a plane is active, any sketch entities you create will be on the active plane. To deactivate a plane, double-click in open space or double-click another plane. In addition to creating 2D and 3D sketches, there are other methods of creating curves. We'll take a look at several of these in the next few lessons, but first, we'll take a look at a special type of curve, the helix. The diameter of a helix is based on a circle. So the first step in creating a helix is to sketch a circle in a regular 2D sketch. Once the circle is complete, access the helix command from the Insert Curve drop-down menu. The parameters that control the helix will appear here in the Property Manager. You can define the helix using a combination of pitch, height, and number of revolutions. Select the appropriate setting from the Defined By list at the top. If you wish to create a spiral, you can also specify this from the list. As you make changes to the parameters, a preview of the helix will appear in the graphics area. At the bottom of the Property Manager, you can choose to add a taper angle to the helix. With the parameters set, you can press OK to complete the helix. You can edit the helix by right-clicking the Helix feature in the Feature Manager. Remember that the diameter is defined in using a circle, so to edit the diameter, you must edit the sketch located below the helix. Later we'll see how a helix is used to model threads. Let's take a look at how to define a curve using XYZ data points. This set of XYZ points is interpreted with respect to the coordinate system of the front plane, just as it's shown in the reference triad. When creating this type of curve, there's no need to begin a sketch. Simply use the Insert drop-down menu under Curve, select Curve through XYZ points. You can also activate this and other curve commands using the icons on the Curves toolbar. I don't use curves often enough to have a toolbar available at all times, so I'll be using the Insert Curve drop-down menu during this course. This is the dialog box where the curve is defined using XYZ coordinates. Data points can either be entered manually in this table or imported from an ASCII text file. First, let's enter a few points manually. To activate the first row, double-click one of the cells. The row will be activated, and each cell will have a value of 0. Also, the units used in the current document are shown. I'll enter values and double-click the next row to activate it. Notice as you activate a new row, the values from the previous row are copied. I'll enter a few more points. And in the graphics area, you can see a preview of the curve as I define it. If you need to insert a point, you can highlight a row and click Insert to add a new row before the highlighted row. When you complete the set of points, you can click OK to complete the curve, or you can save the data for later use. If you save the data, the file created will have the extension SLDCRV. I'll click OK, and you can see the completed curve. This curve can be used for several things, such as a path for a sweep or a guide curve for a loft. In the Feature Manager tree, you'll see an entry labeled Curve. You can right-click and edit this curve just like any other feature. Now let's create a curve using a text file instead of manually entering each point. I'll open the curve through XYZ Points dialog box once again and select the Browse option. In the Files of Type field, you will see two options, SLD, CRV, and TXT. The first option allows you to browse for a set of points that have been previously saved. The TXT option allows you to import data from an ASCII text file, with XYZ columns separated by a space or tab. You can create this type of file using Notepad or another generic text editor. But if you use a spreadsheet program like Microsoft Excel, you can quickly generate data points using equations and other spreadsheet features. Here I have an Excel spreadsheet with 3 columns. The second and third columns are defined using equations. Before using this file in SolidWorks, I have to save it as a text file. I'll select the Tab Delimited Text File option from the Save as Type field. Notice I didn't specify units in the spreadsheet. When I import this data into SolidWorks, the units from the active document will be used. Let's import the curve and you'll see what I mean. In SolidWorks, now I'll insert a curve through XYZ points and browse for the file I just created. Remember, I saved a text file, so I have to change the files of type field to txt. Once I open the file, notice the points are imported and the units have been set based on the units that I'm using in this document. I'll click OK, and there you see the resulting curve. Sometimes, rather than creating 3D sketches, it's easier to create 2 or more regular sketches and combine them using the Composite Curve command. Here I have 2 sketches, one on the top plane and one on the front plane. Right now, they're 2 separate entities. This can be a problem in certain situations. For example, if I create a sweep, the profile will only follow one sketch. It won't profile from one to the other. By combining them into a single curve, the result is quite different. Let's take a look at how sketches can be merged. Here again, I have the 2 separate sketches. From the Insert drop-down menu, I'll select Curve, then Composite. The Composite Curve Property Manager comes up with a single selection window. You can select sketches either from the Graphics window or the Feature Manager. As long as the sketches are touching, forming a continuous curve, they can be combined using this command. With both sketches selected, I'll click OK, and you can see in Feature Manager tree, the 2 sketches have been combined into a single composite curve. Note that the Composite Curve command is not limited to combining sketches. You can also select model edges. In this example, I'll combine this sketch with several edges on this model. As you select edges, they're added to the selection window. I'll click OK, and the composite curve is complete. Another type of curve you can create is a curve through reference points. This type of curve is defined by existing points, either sketch points, endpoints of lines, vertexes, almost any type of selectable point. Here I have a 3D sketch. What I want to do is create a smooth curve along the path of the sketch. This can be useful for modeling cables or tubing. Although I'll be using a 3D sketch as a reference in this example, it's important to note that I'm not editing the sketch. Curves are created outside of sketches. In fact, if you're editing a sketch, the curve commands will not be available. From the Insert drop-down menu, I'll select Curve and Curve through reference points. Once the selection window comes up, I'll click the endpoints of these lines, and you can see a preview of the curve. If you wish to close the curve, you can do so by checking the Closed Curve box in the Property Manager. There are 2 uses for projected curves: to take a 2D sketch and map it onto a surface, and to combine 2 sketches and do a single 3D curve. First, let's take a look at mapping a sketch onto a surface. Here I have a sketch already created on the front plane and a surface. This is an extruded surface, but it can be any type of surface, including any face of a model. You'll find the Projected Curve command on the Insert, Curve drop-down menu. In the Property Manager, you can select one of the 2 types of projections. In this case, I'll use Sketch on Face. In the first selection window, I'll select the sketch to project. You can do this from the Feature Manager or the Graphics window. In the next selection window, I'll select the face I want to project onto. This can be one or more faces. An arrow will appear indicating the direction in which the sketch is being projected. To change this direction, you can click the arrow in the Graphics area or use the Reverse Projection checkbox in the Property Manager. To complete the curve, I'll click OK, and you can see the resulting curve on the surface. Next, let's use the same Projected Curve command to combine 2 sketches. These are regular 2D sketches, one on the top plane and one on the front plane. When using this command, the 2 sketch planes have to intersect. They can't be parallel to each other. I'll launch the Projected Curve command, and this time select the Sketch onto Sketch option. Once the sketches are selected, you'll see a preview of the projected curve. I'll click OK, and the curve is complete. The final type of curve we'll take a look at is the intersection curve. This is quite different from the other curves we've seen so far. The other curves were listed in the Feature Manager tree as curves, not sketches. The intersection curve is actually a sketch tool. It's used to generate curves within sketches, as you'll see in the following examples. Let's start by creating a curve at the intersection of a plane and a surface. I have a planar surface here, but this could be any type of surface or model face that intersects a plane. The intersection curve is found on the Tools drop-down menu in the Sketch Tools section, or it's found under the Convert Entities drop-down icon. Notice as soon as I selected the command, the Property Manager appears showing only a selection box. From the Feature Manager, I'll select the front plane and the planar surface. When I click OK, the intersection curve is created, and I'm placed into Edit Sketch mode for a 3D sketch that was just created. The only problem with this is that if I want to continue working on this sketch, I'm stuck with a 3D sketch, even if I don't need one. I can avoid the 3D sketch by selecting a plane before launching the Intersection Curve command. Let me cancel the sketch and start over. First, I'll select the front plane from the Feature Manager tree and click on the Intersection Curve icon. Now all I have to do is select the planar surface to generate the intersection curve. Once I press OK, a new sketch is started, but it's a regular 2D sketch. Keep in mind, I can create an intersection curve between a plane, the front plane in this example, and any surface or model face that intersects it. In fact, if you needed to, you can create an intersection curve between a plane and an entire part. Just select a plane, launch the Intersection Curve command, and instead of clicking a face from the graphics area, select the part icon in the Feature Manager tree. In the last examples, I used a plane to create intersection curves. You don't have to use a plane. You can create intersections between two surfaces or faces like these here. Instead of pre-selecting a plane, I'll launch the Intersection Curve command and then select both surfaces. When using fillets, there are some options that are seldom used, but can be helpful if you understand how they work. Let's spend a few moments reviewing what each of these options does by taking a look at simple examples using the standard constant radius fillet. First, let's take a look at setback parameters. If you create a fillet on three edges that come together at a vertex, you have the option to control how these three fillets will blend together. Without using setback parameters, this is the result you would get. I'll recreate the fillet, this time using setback parameters. With all three edges selected, I can now activate the vertex selection window and pick the corner point. When I do, three edges appear in the setback distances window. I'll enter a setback distance of 1 inch and click the Set All button. The 1 inch setback is applied to all three edges. What I'd like to do is set a smaller distance for the vertical edge. As I click the edges in the list, you'll see an arrow appear in the graphics area indicating which item in the list corresponds to which edge. With the vertical edge selected, I'll enter a value of 0.25 and press Enter. You can already see the preview showing a smaller transition on the vertical edge compared to the other edges. I'll click OK and the fillet is complete. Next, let's take a look at the Keep Features option. This option controls how a fillet will affect features that are near the fillet region. In this example, there's an extrusion near this edge. If I create a large fillet here, what should happen to the extrusion? If I apply a 1 inch fillet using the default setting of Keep Features, the feature will be extended so it remains attached to the part. If instead I clear the Keep Features option, the extrude feature will be completely eliminated by the fillet. Below the Keep Features options, there is the Round Corners option. This allows you to automatically break sharp edges that result when a fillet is applied to sharp corners. If the same fillet is created using the round corners option, the sharp corners are replaced with smooth edges. The last option we'll take a look at is overflow type. What happens when a fillet is large enough that it overflows off of a face? You have two options when this situation occurs. You can keep the existing edge, as you see here, or you can keep the fillet surface, which will cause the existing edge to be modified. The default setting in SolidWorks will allow the software to choose either option. If you wish to force one result or the other, simply select the one you like in the Property Manager. Variable radius fillets play an important role in designing consumer products and other complex shapes. Their simplest application is to create a fillet along an edge that changes in radius from one side to the other. Let's take a look at how to define a fillet like this. Like any other fillet, you start a variable radius fillet by clicking the fillet icon. I'll select the variable radius option in the Property Manager. Notice the full preview option is enabled. This will make it easy to see the effect of some of the options we'll be talking about. I begin by selecting this edge to apply the fillet. A variable radius fillet is defined by assigning radius values to two or more vertices. In this case, you can see two radius flags pointing to either end of the edge I selected. Neither of them has been assigned a value, as you can see. To assign a value, you can enter a radius here in the Property Manager. But how do you know which vertex you're defining? One way is to select the vertex from the list of vertices that appears in the Property Manager. When I click V1 in the list, notice one of the flags is highlighted in the graphics area. Now when I enter a value and press Enter, you can see a radius has been assigned. I'll highlight the next vertex in the list, enter a radius, and press Enter. We'll take a look at some other options in a moment, but first, let's concentrate on the effect of this transition setting here. If you take a look at the preview in the graphics area, you'll notice that the edge of the fillet is a smooth curve connecting the two radii. If I change the setting to straight transition, notice the edge of the fillet is a straight line. Of course, choosing the proper setting is entirely up to you and what your design calls for, but you should be aware of this setting in case you're not getting the results you expect. I'll click OK to accept these settings. Next, let's add another variable radius fillet to take a look at another important option. This time, I'll select the lower edge and I'll assign values to each vertex. Notice that instead of entering values in the Property Manager like I did before, I'll double-click the flags in the graphics area to specify each radius. After entering a value, I'll press Enter to see a preview. Notice there are points that appear along this edge. These are available control points that I can use to further vary the radius of the fillet along the edge. To remove or to add more of these available control points, I can change this value in the Property Manager. Although these control points are available, they are not active. Right now, I only have two control points, the two vertices. To activate one of these intermediate points, I have to select it in the graphics area. When I do, a flag appears allowing me to enter two values, a radius and a percentage value. This percentage represents how far along the edge this control point is located. At 50%, the point is located halfway along the edge. This can be a great tool, especially if you're working on a curved edge where it might be difficult to locate the exact center. Just type in 50% or whatever value you're interested in, and SolidWorks will find it for you. I'll click OK and complete the fillet. Finally, I'll add one more variable radius fillet to demonstrate a convenient way to specify values for multiple points. I'll click the fillet icon and select variable radius for the fillet type, and I'll select this edge. Notice that because tangent propagation is enabled, one fillet will propagate all around. However, if I don't select the other edges, I won't be able to specify values at these other points. To enable these points, I'll select each edge, and you can see each point will have a flag for me to specify a value. This is when it can be convenient to use the Set Unassigned and Set All button in the Property Manager. Suppose I want every point to have a radius of 0.1, except two of these points. Well, rather than double-clicking each flag to enter a value, I can enter the 0.1 value and click the Set Unassigned button. Because none of the points had a value assigned, they have all taken on the 0.1 value. If you wish to make a change that affects all of these points, you can enter a value, 0.25 in this case, and click Set All. This will cause even the already assigned values to change. Finally, I'll double-click a couple of points and change their values. Then click OK to complete the fillet. Face fillets have several uses. They can span across small gaps. They can be useful in blending complex surfaces, and they can be defined by a boundary line instead of a radius. Let's take a look at an example of spanning across a gap. Sometimes a complicated model can end up with small gaps without you knowing. This can also be a result of bad imported geometry. In this case, I've created an example that has one of those difficult to detect gaps. If I attempt to create a fillet on this edge, you can see by the preview that something is wrong. In fact, if I zoom in, you can see that there is a tiny gap between these two faces. In the case of a complex model, it can be difficult to find the cause of a gap like this. Instead of trying to fix this, you can use a face fillet to blend the two faces across the gap. I'll select the fillet icon and change the fillet type to face fillet. I'll specify the radius and select the two faces that I wish to blend. Notice that each face must be selected into a separate selection window. The selections will be color-coded matching their corresponding window. I'll click OK and the fillet is complete. There are times when you need to create a fillet and you don't care what size it is, as long as it ends at a certain point. For example, in this part, I want to fillet this edge. The size isn't important. Instead, the important thing is that the fillet completely eliminates this face, ending right at this edge. The face fillet allows me to do this. I'll select the fillet icon and change the type to face fillet. I'll select the two faces into the selection windows. But I won't worry about entering a specific value. Instead, I'll expand the Fillet Options section in the Property Manager. In the Holding Line section window, I'll select this edge. The fillet will automatically adjust so it ends precisely at the edge I selected. This would be impossible to do with a constant radius fillet. Although fillets create tangent surfaces, they don't create curvature continuous surfaces. Let's take a look at this part. I have two solid bodies that are identical in every way, except one has a regular fillet and one has a curvature continuous face fillet. You may not be able to tell the difference, but watch when I display the curvature of each face. This display allows you to see changes in curvature as different colors. Notice this body shows a gradual change in curvature from the lower face through the fillet face. This body displays two completely different curvatures that change sharply where the two faces meet. The curvature continuous fillet is a type of fillet face. I'll edit this fillet, and down here in the Property Manager, you can see the option for curvature continuous. You should be aware that this type of fillet is generally more difficult and time-consuming to manufacture, so you'll want to use it sparingly to keep manufacturing costs down. When you need to create a full round fillet on a part like this here, there's a special fillet type you can use rather than creating one fillet on each side. This is especially helpful if the fillet has to vary in radius. To use the full round fillet, just click the fillet icon and select Full Round in the Property Manager. You'll be prompted to select at least 3 faces that identify the round. In the first section, you'll select one side of the round, then the face you wish to eliminate with the round, and finally the other side of the round. You'll see a preview, and as with other fillets, if the edges are tangent, the fillet will propagate as long as the option is enabled. Adding fillets can often be a tedious process, especially when the geometry you're working with is complex. Fillet Expert makes the filleting process more flexible, allowing you to create multiple fillets at the same time, resolving geometry problems and making it possible to selectively resize fillets you've already created. Let's take a look at these capabilities using this sample part. Fillet Expert is not a separate feature, but rather added functionality within the fillet feature you're already familiar with. I'll launch the fillet feature to bring up the Fillet Property Manager. At the very top, you have the option to select Fillet Expert. When it's selected, the Property Manager changes slightly. Notice the different types of fillets are no longer listed. Fillet Expert functionality is only available for constant radius fillets. In fact, if a fillet type other than constant radius is selected, the Fillet Expert button will not be available. First, let's take a look at the benefit of having the Apply button available in Fillet Expert. I can enter a radius value, 0.25 in this case, select the cyan-colored face and click Apply. The fillet has been applied, but the Property Manager is still here, making it possible for me to continue adding more fillets without restarting the fillet feature. I'll select the magenta-colored face and click Apply again. To dismiss the Property Manager, I'll click OK. Notice two individual fillets have been created. This is important to note. If you intended for these to be a single feature, you could have selected the cyan face together with the magenta face before applying the fillet. Fillet Expert can also automatically invoke Feature Expert when necessary. I'll launch the fillet feature once again. Notice the Property Manager is already showing Fillet Expert. This setting is remembered from the last time I used the fillet feature. This time, I'll select the two brown faces. And click Apply. Because we're using Fillet Expert, the errors are automatically resolved by invoking the use of Feature Expert. When I click OK, you can see two additional fillets have been added. Let's launch the Fillet feature once again to see another powerful application of Fillet Expert. Earlier, I added a fillet on this cylindrical feature by selecting the cylindrical face. This means that a single fillet feature is responsible for two edges being filleted. What I'd like to do now is change the fillet radius on just one of the two edges. In the past, I'd have to edit the fillet, redefine it so it only contained one edge. Then I could create a second fillet to control the radius of the second edge. This procedure is not difficult, but it can be time-consuming. Now we no longer have to go through this process. All we do is enable the Change tab in the Property Manager and select the fillet that we wish to change. I'll enter a value of 1 inch and click Resize. I can also select Filleted Edge and click Remove. Fillet Expert will make any necessary changes to my Feature Manager tree, such as creating new fillet features, deleting features, or reordering features as required. Before I click OK, notice I also have the ability to select sets of fillets using their radius value here in the existing fillets list. This is a convenient way of making changes to all fillets having the same radius. At this point, I'll click OK, and you can see that what used to be a single feature controlling the size of both fillets on the cylindrical boss has been broken up into two separate features automatically. Before wrapping up, I'd like to show you how to use a tool called Corner Expert. Here I have a simple L-shaped block with a couple constant radius fillets along the edges of the block. Since SolidWorks is a history-based modeler, the order in which you apply the fillets will affect what the end result here looks like.
To make this easier for the designers, SolidWorks created the Corner Expert to help you visually choose the end result without having to think about the order the fillets are applied in. Let's take a look. I'll launch the Fillet Expert again and click on the Corners tab. In order to create a corner fillet, you must select a corner face where 3 filleted edges meet at a single vertex or point. However, there are a couple rules to this, which I'll explain in a moment. For now, I'll select this corner here. With the corner face selected, I can click the Show Alternatives button, and the Corner Expert shows me previews for how this corner can be created. The previews make it easy to graphically choose the result I want, without having to think about the correct order you'd need to apply the features in order to create it. I'll choose one of the previews, and the corner is done. The Copy Targets box lets you quickly copy the corner fillet settings to other similar corners of your model. I'll select the corner that I want to copy in the Corner Faces box. Next, I'll click in the Copy Target selection box to activate it. The Enable Highlighting checkbox will highlight all the compatible corners in the graphics area. I'll select the opposite corner on the model as the destination face, and I'll click the Copy To button to copy the corner settings. You can see that the Corner Expert makes it easy to visualize the end result of your fillets without having to think about how they're ordered in the Feature Manager tree. But as I mentioned earlier, there are some tricks to using it. You might notice that not every corner is selectable with the Corner Expert. If I try to select this corner, you can see from the cursor feedback that the Corner Expert won't let me. In order to use the Corner Expert, the fillets must have different convexities. There are really 2 classes of fillets. Some fillets that add material and some fillets that remove material. These are sometimes referred to as internal versus external fillets, concave versus convex fillets, or fillets versus round. For this corner, notice that the fillets are all rounded outward. However, the corner we selected earlier worked because it has a mix of internal and external fillets meeting at the same point. The Sweep feature is one of the basic features available in SolidWorks that allows you to generate solid geometry. It can be used to create simple geometry as well as complex shapes. A sweep is composed of 2 items, a profile and a path. The profile controls the shape of the sweep, while the path controls its direction. Take a look at this angled cylinder. This was created using a simple sweep, with the circle as the profile and an angled line as the path. By making the path a bit more complex, you can see a sweep allows you to create shapes you wouldn't be able to create using simpler features such as the extrude or revolve. To take the sweep feature to the next level of complexity, you can add what are called guide curves. These curves control the size of the profile as it's swept along the path. Here, for instance, the elliptical profile varies in size along the path because it's controlled by a guide curve. Although only one guide curve is used here, you can have as many guide curves as you need. We'll be taking a look at how to use sweeps in the next few lessons. We'll begin with a basic sweep that incorporates some advanced options such as guide curves and end tangency as we go along. The basic sweep requires 2 elements, a profile and a path. A profile is a sketch that defines the cross-sectional shape of the sweep. In this example, the profile sketch is a circle. A path is used to control the direction of the profile. In this example, a sketch is used to control the path. We'll see later that a path can be something other than a sketch, but for this basic example, a sketch is used to define the path. There are some important differences between sweeps and the basic extrude and revolve features you may be more familiar with. Let's take a look at these differences by creating a basic sweep from scratch. When you begin a new part, the only available icons on the Features toolbar are the extrude and revolve features. The sweep icon is not available. Remember that a sweep requires 2 elements, a profile and a path. SolidWorks knows that at the moment I have neither, so it wouldn't make sense for the sweep icon to be available at this point. To activate the sweep icon, you first have to create both a profile and a path. Let's concentrate first on creating the sweep profile. I'll begin a new sketch on the front plane and sketch a circle.
As with other features, it's not necessary to dimension the sketch before completing the feature. All I need for the sweep profile is a circle, so I'll exit the sketch. Next, we'll create the sweep path. For this, I'll begin a new sketch on the top plane. It's very important that you understand we are now working on a new sketch that's completely separate from the first sketch. In this new sketch, I'll create a line and a tangent arc to serve as our path. And put in some dimensions. Notice that even at this point, although the path is essentially complete, the sweep icon is still not active on the Features toolbar. To be able to use the sweep feature, I must have a profile sketch and a path sketch, and I must exit out of all sketches. In other words, I cannot be in Edit Sketch mode. I'll exit the sketch, and now you see the sweep icon is available. I'll click on it, and we'll see the Sweep Property Manager appear. At the top of the Property Manager, you will see two selection boxes. The first is where you select the sketch you wish to use as a profile, and the second is where you select a sketch to be used as the path. If you forget which goes where, simply hold your pointer over the blank section box and a tooltip will appear telling you what is required. You may also notice that one of these selection boxes may already contain a sketch, although you did not select one. This will happen if you select the sweep icon immediately after exiting a sketch. In this case, I had just exited the path sketch when I clicked the sweep icon, so SolidWorks placed the sketch into the path selection box. If you're wondering how SolidWorks knew this was the path sketch and not the profile sketch, it assumes a sketch containing an open contour will be used for a path, while a closed contour will be used for a profile. Since the path sketch is already selected, all I have to do is select the profile sketch. I can do that by clicking on the circle itself, or by selecting the sketch from the Feature Manager tree. To be sure the correct sketches are selected, SolidWorks will color code them for you as you indicated in the Property Manager. The blue sketch is your profile, while the pink sketch is your path. In case you made a mistake with your selections, you can easily remove an item from the selection window using one of several methods. The easiest is to simply click the selected sketch in the graphics area. This works like a toggle switch. One click selects the sketch, another deselects the sketch. You can also right-click the selection box and pick Clear Selections. And you can right-click in the box and press Delete on your keyboard. Any of these methods will work. As you make your selections, be sure the appropriate selection box is active. As with other selection boxes in SolidWorks, you know which one is active because it is highlighted. With the sweep feature, once you select a profile, the path selection box is automatically activated so you can quickly make your next selection. With both the profile and path sketches selected, I'll click OK and the simple sweep is complete. A sweep profile must be created as a sketch. A path, however, can be one of several items. In this lesson, we'll take a look at the various items that can be used as sweep paths. The simplest type of path is a 2D sketch. The sketch can be an open profile as you see here, or a closed profile like a circle. It can be useful in some cases to have a path that is not attached to the profile. Here, for example, a sweep can be created despite the distance between the profile and path. In addition to using sketches as paths, you can also use existing model edges. Here, for instance, the circle is swept along the edge of the block. If you have multiple contours in your profile sketch, they will each be swept along the path. Here, for example, each of the circles will be swept along the edge of the block. When you create a sweep, you will notice that the path selection box in the Property Manager is limited to a single item. If you wish to sweep a profile along several edges, you can do so by using Smart Selection. Here I wish to keep the rectangular sketch around every edge of the solid body. I'll launch the sweep command and select the rectangle as the sweep profile. Instead of selecting the edge as the path, I'll right-click on the edge and choose Selection Manager. With the Selection Manager active, I'll use the Select Group option and begin clicking on the edge segments I would like to include in the sweep. When I'm done selecting edge segments, I'll click OK, and the items I choose will become this sweep path. In addition to using sketches and model edges as sweep paths, you can also use curves, such as projected curves, curves through free points, and curves through reference points as you see here. The circular sketch here will be used as the sweep profile, while the curve will be used as the path. By knowing the various types of entities that can be used as sweep paths, you can save time by avoiding the creation of sketches if they aren't necessary. You will also be able to apply sweeps in more scenarios, such as the modeling of tubing and wiring. Guide curves used with the sweep feature allow you to vary the size of the profile as it is swept along its path. Let's take a look at a simple example of this. Here I have two sketches, a circle sketched on the top plane and a vertical line sketched on the front plane. Before I click the sweep icon, I want to create a third sketch to be used as a guide curve. I'll start a new sketch on the front plane. The sketch will be a 3-point arc. When you sketch a guide curve, it must be attached to the profile somehow. In other words, I cannot have a guide curve like this. The sketch has to touch the profile like this. To ensure the curve is attached to the profile, you can use a special geometric relation called pierce. To use the pierce relation, keep one important item in mind. The pierce relation is only available between a point and a curve. If you select 2 points, the pierce relation will not be available. You must select a point and a curve such as a sketch entity. Here I'll select the endpoint of the arc, the point, and the circle from the profile sketch, the curve. You can see the pierce relation appear in the Property Manager. I'll select it, and now I'm sure the point is exactly on the circle. Before I exit the guide curve sketch, there are some things you should know about the length of the guide curve and path. Essentially, the sweep will only go as far as the shortest curve, whether it's the path or the guide curve. If you have a situation where you're using multiple guide curves, the shortest one will control the length of the sweep. In this case, I want the sweep to be as long as the path. So to make sure the guide curve is at least as long as the path, I will create a horizontal relation between the endpoint of the arc and the endpoint of the path. Although it's not necessary, I'll add a couple of dimensions to control the guide curve. I'll dimension the path to establish the size of the sweep at the top, and to control the curvature of the arc, I'll dimension its radius. With the guide curve fully defined, I'll exit the sketch and click the sweep icon. I'll select the profile and the path. To use the guide curve, I'll expand the guide curve section and select the other sketch. You can immediately see the preview update. I'll click OK, and the sweep with the guide curve is complete. Before we conclude this lesson, I want to point out an important detail when working with guide curves. Remember, the purpose of guide curves is to change the size of the profile as it is swept along a path. Let me edit the profile sketch. Notice the circle is not dimensioned. If I add a dimension to the circle, as soon as I exit the sketch, the sweep will not work. Consider that when the circle has a diameter defined with a dimension, the guide curve cannot change this diameter as it's swept along the path. In most cases, fully defining your profile sketch defeats the purpose of using guide curves. One more thing I want to mention. In this example, I sketched the profile before sketching the path or guide curve. If you sketch the path or guide curves first, you can use them as guidelines as you create the profile. If you intend to use guide curves, I highly recommend you sketch them before sketching your profile. This will help you avoid using dimensions and relations on your profile that may accidentally restrict your use of guide curves as we just saw. This is only a recommendation, but one that can help you out of trouble when using guide curves. By using more than one guide curve, you can create very complex shapes. You could also run into problems that will cause your sweep to fail. Most failures are a result of profiles that are too rigid. Let's take a look at an example. Here I have a part with 4 sketches, a vertical line to be used as a path, 2 separate sketches to be used as guide curves, and a circle to be used as the profile for a sweep. I'll click the sweep icon and select the profile and path. Next, I'll select the first guide curve, and the preview of the resulting geometry appears. Next, I'll select the second guide curve, and the preview disappears entirely. Whenever a preview disappears, you can be sure there's a problem. If I click OK, I get an error message and the sweep fails. To be certain there isn't a problem with the second guide curve, let me deselect the first guide curve. As you can see by the preview, the second guide curve appears to be fine. So what is the problem with using both guide curves? Well, the problem is that the profile sketch, a simple circle, is too rigid to take advantage of both guide curves. Notice what the guide curves are doing here is controlling the radius of the circle. At a point about halfway up the path, one guide curve is forcing the radius of the circle to be very small, while at the same time, the other guide curve is trying to make the radius very large. This poses a conflict since the circle can only have one radius. In fact, if the guide curves were to deform the profile, you would end up with an ellipse, not a circle. To correct this problem, you simply have to make a change to the profile sketch. You have to give it the freedom to be able to follow both guide curves. And in this case, changing the profile from a circle to an ellipse will do the trick. As you add more guide curves, you will likely have to go to an even more unrestricted profile sketch, a spline. In this example, a third guide curve has been added. In order for the profile to follow all 3 curves, a spline was used. When you use the sweep feature, there are several options available that will affect the resulting geometry. These options include the use of guide curves, twist, tangency, and orientation. In this lesson, we'll take a look at the use of different orientation types. Although the majority of the time you will likely be using the default orientation known as follow path, it's helpful to understand the effect of using the other orientations. Let's begin by comparing these 2 individual sweep features. Although they appear quite different, they were actually created using identical profiles and paths. The difference in the resulting geometry is due to the behavior of the profiles as they are swept along their paths. In the first example, the orientation of the circular profile follows the path. As the path transitions from a straight line to a curve, the profile changes orientation to follow. This is the default behavior of a sweep and is referred to as follow path. The second example, you can see that as the path transitions from a straight line to a curve, the profile orientation does not change direction with the path. It maintains the same direction as the original sketch plane of the profile. This behavior is called keep normal constant. To make this clear, take a look at a cross-section view. Notice that at any point along the path, the cross-section is always the same. If I edit this sweep feature, you can see in the options section, there's a list of available orientation and twist types. Currently, the Keep Normal Constant option is selected. If I change this to the default follow path setting and click OK, you see the result is now identical to the first sweep. Once you've experimented a couple of times with the follow path and keep normal constant options, you'll quickly understand the difference between them, and you'll be able to decide rather easily when to use each one. Unfortunately, the same cannot be said about the next available options. For many users, the settings called Follow Path and First Guide Curve and Follow First and Second Guide Curves simply become something to try if nothing else seems to work. Let me try to explain the idea behind these settings and hopefully make them less mysterious and maybe even useful for you. I'll start with this simple sweep. It's a triangular profile swept along a straight line. I'll edit this sweep and use this sketch as a guide curve. Notice that although the triangular profile now follows the guide curve, the overall triangular shape is not twisted. That is, the edge that was horizontal to begin with remains horizontal at the end of the sweep. Now let's edit the sweep again. And this time change the orientation to Follow Path and First Guide Curve. Now you can see that the profile not only follows the guide curve, but it is twisted. The edge that used to be horizontal no longer is. So why is that? And how is the twist angle defined? Let's edit the sweep once again and change the orientation back to Follow Path. To help explain this, I have two sketches I'll show, as well as a couple of reference dimensions. The lines I have here connect the path to the guide curve. You can see that in the initial profile, the angle between the line and the horizontal edge is 90 degrees. At the end of the sweep, you see the angle has changed quite a bit. Now let's change the orientation to Follow Path and First Guide Curve. Notice the angle at the end face of the sweep is now the same as it was in the beginning. By selecting Follow Path and First Guide Curve, you're instructing SolidWorks to twist the profile as it's swept along so this angle stays the same. This may not seem very important to you at the moment, but you would be surprised at how many times users will add guide curve after guide curve in an attempt to end with this exact result, simply because they don't understand how the setting works. If you understand the principle behind the setting, the same thing applies to Follow First and Second Guide Curves, except this line is defined by connecting the first guide curve to a second guide curve instead of the path. In addition to controlling the behavior of a sweep profile with guide curves, you can also have a profile twist as it's swept along a path. Let's take a look at how this is done. I already have two sketches in place, so I can click the sweep icon to begin. I'll select the profile and path, and a preview of this simple sweep appears. In the Property Manager, I'll expand the Options section and select Twist Along Path from the Orientation list. The characteristics of the twisting behavior can be specified in number of turns, degrees, or radians. I'll select turns for this example. You can see the resulting geometry is drastically different. This is a useful feature to be familiar with, especially if it's going to save you from having to create complex guide curves. Take this model for instance. Creating this without the use of the twist can be quite a challenge. The sweep path used here is a circle, and the twisting is taken care of through the use of the Twist Along Path option. The Twist Along Path option can also be combined with Keep Normal Constant to further control the behavior of the sweep. Take a look at this part. This is a sweep using a rectangular profile, an arc as a path, and the Twist Along Path orientation setting. If I create a section view that runs parallel to the profile sketch plane, you can see the intermediate profiles are quite different in shape than the rectangular profile. Let me edit the sweep and enable the twist along path with normal constant option. This shape will take a second for SolidWorks to generate, but it's normal as your geometry gets more and more complex for features to take longer to rebuild. Take another look at that section view. Notice this time the intermediate profiles are the exact same shape as the original. Although our focus thus far has been on creating geometry with sweeps, you also have the option of removing geometry by using the Cut Sweep feature. The sketch requirements for the cut sweep are the same as those for a regular sweep. You need a profile and a path. The profile is defined in a sketch, while the path can be a sketch, a curve, or an existing model edge. In this example, I want to trim away the sharp edge of this part to create a nicer looking finish. I already have a sketch in place to be used as my sweep profile. It was created on a plane defined as normal to this edge of the model. Once activated, the property manager for the cut sweep should look familiar. It's identical to that of the regular sweep. I'll select the profile and the path. Notice a preview shows up, but it only goes as far as the first segment of the model edge. Since the edge is made up of tangent segments, I can use the tangent propagation setting in the options section of the property manager to get the cut to propagate along the entire edge. If your preview does not update, you can simply deselect and reselect the path. At this point, I can click OK and the cut sweep is complete. Before we continue, I want to return to the Cut Sweep Property Manager and point out a setting that is very important in situations like this one. The setting is called Align with End Faces, and it's found in the Options section of both regular and cut sweeps. I'll uncheck this setting and click OK so we can examine the results. Notice the cut sweep only goes as far as the path I selected. In most situations, you don't want to be left with extra material like this. By default, SolidWorks will extend the sweep up to the next available face. However, this only happens if the Align with End Faces option is enabled. In this lesson, I'll introduce you to a method of creating threads. Here we have a plastic bottle, and we'll be adding an external thread to go along the mouth. Modeling threads in SolidWorks is a three-step process. First, you have to create a helix that defines the thread pitch. Second, you must define the thread profile. Third, you must terminate the thread to eliminate the abrupt ends. Let's begin by creating the helix for a sample thread. The helix will be based on a circular sketch. Often the dimension from the top of the bottle to the top of the thread is important. Because of this, rather than sketching a circle on the top face of the bottle, I'll create a plane offset from the top surface. Next, I'll begin a sketch on the newly created plane, and I'll convert the top edge of the bottle to generate a circle. With the circle in place, I can launch the helix feature from the Insert, Curve drop-down menu. The helix will be defined by pitch and revolution. I'll specify a constant pitch and a number of revolutions starting at 0 degrees. Then click OK. Now that the threads path is created, I'll move on to creating the thread profile. This will be the cross-sectional shape of the thread itself. I'll create a new plane that is normal to the end of the helix. This will provide the correct orientation for the cross-section. And I'll sketch the thread profile on the new plane. Sketching the thread profile is the most time-consuming step in creating a thread. Since thread profiles are likely to be reused, consider saving them to your design library for quick access.
You'll want to make sure the sketch for the thread profile is fully defined. That way you can be sure the resulting thread geometry is exactly what you're looking for. I'll continue adding dimensions and relations to fully define the sketch.
Note the overlap of the thread profile into the body of the bottle. This is important. Without the overlap, the contact area between the thread profile and the bottle could result in zero thickness geometry, generating an error. With the thread profile complete, I'll exit the sketch and create a sweep feature. The sweep profile will be the thread profile sketch, and the path will be the helix. I'll click OK, and the thread is nearly complete. It's important to notice that to create this external thread, we're simply adding a sweep feature. The same process can be used to create an internal thread, but by instead applying a swept cut to remove material. At this point, all that remains is to terminate the ends of the thread. There are several techniques for doing this. One of the more common approaches is to use a revolve feature. I'll begin a sketch on the starting face of the thread. The profile I'll be revolving is the shape of the thread itself. Using the Convert Entities tool is a quick way to capture the shape. However, note that converting the face itself can cause a problem. The lower edge of the profile is not linear, so it can't be used as an axis of revolution. I'll use Convert Entities with the original sketch selected from the Feature Manager tree. This gives me the profile I need. I'll launch the Revolve feature, and I'll use the lower edge as the axis of revolution. If you want to have a more gradual termination, you can always increase the radius of the revolve. You can do this by adding a center line at a distance from the profile sketch. The revolve only needs to go 100 degrees to merge into the body of the bottle. You can see this in a top view. If you want to make sure the revolved feature completely merges with the bottle, extend it well beyond the bottle surface, then as a second step, you can cut away any material that protrudes on the inside. This completes one end of the thread. The other end is a bit more complicated because we don't have the original sketch available for use as a reference. There are several ways to overcome this. The approach I'll use is to simply reuse the sketch from the other end of the thread. I'll do this using the little-known Derived sketch command. I'll select the end face of the thread along with the sketch used previously for the revolve. I'll then click Derived Sketch from the Insert drop-down menu. To position the sketch properly, I'll add a couple of geometric relations. And the sketch is complete. Note that this derived sketch is controlled entirely by the original sketch. Once it's in position, it is fully defined without the need for dimensions. I'll create another revolve to complete the thread. And there you go. We get exactly what we were looking for. The loft is perhaps the most flexible feature SolidWorks provides for the creation of geometry. It can be used to create anything from simple prismatic blocks or the most complex of surfaces. The basic loft allows you to create geometry by defining two cross-sections and joining them together. Here, for instance, I have a loft between a circle and a square. This ability to change the cross-sectional shape of a solid is what separates the loft feature from the sweep feature. When using a sweep, although you can vary the dimensions of the cross-sections, the shape must remain constant. Notice here as we look at the cross-sectional shape of this sweep, it changes in size, but it's always elliptical in shape. This limitation is not present when using a loft. In the next few lessons, we'll take a look at different applications for the loft, as well as the various methods of defining the feature. The building blocks for a loft are the profiles used to define its cross-sectional shape. When you begin a part from scratch, these profiles are typically in the form of 2D sketches. As we'll see later, there are other items you can use to define loft cross-sections, but for now we'll stick to 2D sketches. For our first loft exercise, I want to create a part like this one from scratch. At first glance, you might wonder why a loft is even necessary. After all, the parts look pretty simple, but there are no complex surfaces, so why bother using a loft? Take a look at the top view. Notice the different size profiles at the base and at the top. If you know the size of the base and the size of the top, but you don't necessarily care about the angles of these two faces, then a loft is ideal for the situation. Let's begin a new part and see why this is the case. Here I have a new part file. The first sketch will be on the top plane. This will be a simple rectangle that will serve as the base profile for our loft. I'll dimension the rectangle to be 5 inches by 2.5 inches. This is all the information I need for this profile, so I'll exit the sketch. Next, I'll create a sketch that will define the top of the loft. The top of the loft is going to be located some distance above the base sketch. In order to create that sketch, I'm going to need a plane located 6 inches above the top plane. I'll create a new plane using the top plane as a reference and specify 6 inches as the offset distance. Now I'm ready to create the top profile. By the way, creating lofts will often require that you create reference planes. If you don't feel comfortable with the various methods of creating planes, take a moment to review the topic in the SolidWorks online help, or in our introductory course, SolidWorks Core Concepts. I'll begin a sketch here on my newly created plane, and I'll define a rectangle 4 inches by 2 inches. At this point, I'll exit the sketch and select the loft icon. The Loft Property Manager appears. The Profile selection window is active and ready for me to select the profiles that will define the loft. I'll need to select 2 or more profiles to define a loft. As with most features, I can either select the items I need from the Feature Manager tree or from the Graphics window. When using a loft, I strongly recommend selecting your profiles from the Graphics window. Here's why. The Loft feature is sensitive to the location where you'll select each profile. I'll select the base profile close to this corner, and I'll select the top profile near the corresponding corner. A preview immediately appears, as well as these green dots called connectors. The reason these connectors join these specific corners of the profiles is because of where I clicked. To make this clear, let me right-click in the Profile selection window and select Clear Selections. Now, I'll repeat the selection process, but this time, I'll click the profiles near opposite corners. Notice the drastically different result? For this reason, you'll want to be careful about where you select your profiles. However, if you do happen to make a mistake, you can click and drag the connector dots from one corner to another and fix any unwanted twisting. At this point, I'll click OK, and the loft is complete. The dimensions of the base and top profiles have been defined, as well as the overall height of the part, and the loft has taken care of everything in between. This is exactly what I was looking to accomplish. An interesting thing will happen if you attempt to create a loft that closes on itself. Here, for instance, I have 4 sketches. I like to create a ring that lofts between each of these shapes. The preview of the loft will update as I select each profile. However, when I reach the end of the ring, instead of closing the loft, the original profile is deselected. This does not mean a loft cannot be closed. When you arrive at the point where each profile has been selected, Instead of clicking the first profile again, go to the Property Manager and find the Close Loft checkbox in the Options section. This will give you the result you're looking for. The use of sketches to define loft profiles is common, but profiles are not strictly limited to 2D sketches. They can be defined in different ways. For instance, you can use existing model faces, surfaces, 3D sketches, and even points as profiles. Here I'm going to use an existing face, a surface, a 2D sketch, and a point, all in the same loft feature. As you can see, there's nothing special you have to do in order to make use of these different types of profiles. The only restriction is when using points, they can only be used at the beginning or end of a loft. In addition to the profile types we've seen so far, a loft feature can also be created using profiles and/or guide curves contained in a single 3D sketch. In this example, I have a couple of rectangular profiles connected by a spline. All of these entities reside in a single 3D sketch. At this point, I'll click the Loft icon to bring up the Loft Property Manager. To assist me in selecting the correct sketch segments in the 3D sketch as the sketch profiles and guide curves, SolidWorks provides the Selection Manager. The Selection Manager appears when clicking on a sketch segment in a loft, sweep, or boundary surface feature. I would like to use the larger rectangle as the first profile. To do this, I can select a sketch segment of the rectangle so the Selection Manager appears, and then use the Closed Loop option to select the rest of the profile. As an alternative, I can also use the Select Group option in the Selection Manager and individually select all the links that make up the rectangle. Once the proper geometry is heightened, click the green check to accept the selection. Repeat the process to select the end profile. I also want to use a guide curve, so I'll activate the Guide Curve selection window and select the spline in the Graphics area. The Selection Manager recognizes this is an open loop, which is what I want, so I'll accept it with the green check. Later we'll talk much more about guide curves, but for now, I'll accept the loft we created using a single 3D sketch. There's one more benefit to using a 3D sketch. I'll go ahead and right-click to edit the loft feature. By using the Drag Sketch button in the Sketch Tools section, you can dynamically change the 3D sketch. After you've made the necessary changes, simply toggle the Drag Sketch button off and click OK to exit Edit Feature mode. This simple loft has been defined such that the base and top profiles are dimensioned, as well as the overall height. However, the behavior of the side faces is not currently controlled. The loft feature simply connected the profiles as efficiently as possible. If you would like to change the appearance of the side faces, one option you have is to apply constraints to either the beginning of the loft, the end of the loft, or both. Let's take a look at how this is done. I'll begin by editing the loft feature and expanding the section labeled Start and Constraints. As you can see, we don't have any constraints currently defined. Let's begin by changing the constraint on the beginning of the loft. I'll select Normal to Profile. A few things change when this is selected. In the Graphics window, you can see the beginning of the loft starts in a direction normal to the profile. You can control how much influence the Normal to Profile setting will have by adjusting this parameter here. The lower the number, the lesser the effect of the setting. The higher the number, the more noticeable the effect will be. Eventually, if you increase the number high enough, the normal effect will lead to some bizarre results. You can also change the direction of the normal to constraint by clicking the reverse direction arrow in the Property Manager. In this case, the preview disappears when I reverse the direction, which tells me these settings will cause the loft to fail. I'll return the parameter to the correct direction and change the value to 1. Notice the Apply to All checkbox here. If I clear this setting, each corner of the profile will have its own drag handle, which tells me I can control the normal to constraint for each point individually. To make changes to each corner, click the drag handle so it becomes highlighted. Any changes you make in the Property Manager apply only to the handle selected. You can also click and drag each handle and immediately see a preview of the resulting geometry. These same options can also be applied to the end of the loft. This time, instead of selecting the Normal to Profile option, I'll select Direction Vector. This allows me to select a direction other than perpendicular to the profile. You can select model edges, sketch entities, axes, just about any item to define a direction vector. I'll select a line on the profile sketch itself, and you can see how the geometry now goes along the direction of the line I selected. Like before, I can use the Property Manager or drag handle to change the influence of this setting. Before wrapping up this session, let's take a look at the draft option we have when using these constraints. I'll disable the end constraint and return the start constraint to a value of 1 applied to all points. To make the draft setting easier to see, I'll change to a front view as well. As you're probably aware, when you create a boss extrude, you can enable draft so that the resulting extrusion will have angled faces. This can be helpful when modeling a part that will be forged or injection molded. I can do something similar here by increasing the value of this draft angle in the Property Manager. Watch the preview as I steadily increase the value of the angle. As the angle increases, you can see the edges of the lofted feature make a larger angle with respect to the vertical direction. If you wish to reverse the direction of the draft, simply click the Reverse Direction button. If you're designing plastic parts, this setting can help ensure that your parts will be able to be pulled out of their mold. Similar to start and end constraints, guide curves allow you to control the behavior of a loft between profiles. Let's take the simple loft and add guide curves to change the way the profiles connect. As you can see, I already have some sketches created that I'll be using as guide curves. Although I'm using 2D sketches here, you can use several items as guide curves, including existing model edges, 3D sketches, and curves. I'll begin by editing the loft feature and expanding the section labeled Guide Curves. I'll select the arc as a guide curve, and immediately you'll see the preview update. Notice the only edge affected by the curve is the purple one. The other edges remain as they were before. There's a reason for this. When you use guide curves, you have to tell SolidWorks what the guide curve should control. You do this by choosing an option from the Guide Curves influence list in the Property Manager. Currently, to next sharp is selected. This means that the guide curve is influencing the geometry from its location to the next sharp corner in the profile. Anything beyond the next sharp corner is left unchanged. If I change this setting to global, the entire model is affected by the guide curve. Next, let's add the other guide curve to the list. The guide curve influence selection will be applied to every curve on the list. So if I choose to next sharp again, only 2 of the edges are affected by the guide curves. Profiles used for creating lofts should have a matching number of segments. That is, a 3-sided profile like this one will loft nicely to another 3-sided profile. Despite the differences in the shape of the individual segments, the loft feature does a nice job of generating smooth surfaces to join them. On the other hand, a 4-sided profile like this will not loft nicely to a 2-sided profile. Although SolidWorks did succeed in generating a loft, a seam appears on one of the faces. SolidWorks has taken this point and mapped it onto the other profile, but I didn't have much control over that process. Typically, you want to have more of a say in how your model ends up looking, so let's take a look at how you can take control over this situation. The first method is to break up your profiles so they do have the same number of segments. Let's edit this sketch and show you how this is done. When you're editing a sketch, you can right-click over any sketch entity and activate the Split Entities tool. When the tool is active, clicking on a sketch segment will split it. In this case, I have to break up the profile so that it has 4 sketch endpoints. This will provide a corresponding point for each of the 4 points in the other profile. Although these points don't have to be sharp vertexes, they must be endpoints of lines, arcs, splines, or other entities. They cannot be sketch points or center points. I'll click the arc in 2 places. I'll turn off the Split Entities tool by pressing Escape on my keyboard. As with any other sketch entities, I can use dimensions or geometric relations to define the exact location of these points. In this case, I won't worry about being too specific. I'll leave the points where they are. There you have one method of correcting a mismatched number of segments. Before exiting the sketch, I should mention that although I edited the sketch after the loft was already created, it would have been wise to fix it before creating the loft. Remember that where I click on a profile is important when creating a loft. If I don't click near corresponding points, the loft may become twisted, like it is now. This is why it would have been wise to break up the profile before creating the sketch. Of course, not all hope is lost. I can edit the existing profile, clear the selected profiles, and reselect them to avoid twisting. Now let's take a look at a different method of correcting a loft made up of profiles with mismatching segments. This time, it's important that the loft already be created in order for this method to work, so I'll create a loft using these segments as they are. Before clicking OK, I'll right-click in the Graphics window and select Show All Connectors. This reveals control points that tell me exactly how SolidWorks will be mapping one profile to another. If I'm not happy with the way SolidWorks has decided to do this, I can simply drag the points along the profile. While this method can be faster than the previous method, where we actually had to edit the sketch, it's not as precise. Notice that unless I snap the control points onto existing corners, I can't be precise with their location. I can't, for instance, specify that I want this point to be located exactly at the midpoint of this arc. One more thing before I click OK. If you wish to add control points, or connectors as they're called, all you have to do is right-click along one of the profiles and select Add Connector. This gives you a new pair of connectors that you can manipulate as you wish. I'll click OK, and the loft is complete. The centerline option provides a way to control how a loft will connect two profiles. Here I have two profiles. If I create a loft between them, SolidWorks will connect the profiles using the shortest path between them. Let me cancel out of this feature and show you how incorporating a centerline can make a drastic difference. I'll create a sketch on the top plane. This sketch will define the path that the loft will take from one profile to the other. I'll use a couple of arcs. One thing to keep in mind about this sketch is that it must intersect each profile. This doesn't mean it has to connect from point to point. It just has to be attached somewhere along the profiles. Now I'll create the loft once again. I'll select the profiles and expand the centerline parameter section to reveal the selection box for the centerline. I'll click the sketch I created, and the preview will update to show the result. If you wish to show how the profile is changing along the centerline, you can click the eyeglass icon in the Property Manager and cycle through different cross-section along the centerline. Lofts can be created using as many profiles as you wish. Here I have a loft that used 4 profiles, each an individual sketch. In addition to creating individual sketches to use as profiles, you can also add profiles after the loft is created. To do this, right-click on one of the faces created by an existing loft and select Add Loft Section from the pop-up menu. A temporary plane will appear, along with drag handles to help you position it. You can drag the plane anywhere along the loft. Notice a profile is shown to indicate what the shape of the cross-section is at the location of the temporary plane. If you move your pointer over the edge of the temporary plane, you'll be able to click and drag to rotate the plane. Once again, a preview of the cross-section that will result. If you wish to be more specific about the location of the loft section, you can select an existing plane as a reference. To do this, check the Use Selected Plane in the Property Manager and choose a plane from the Feature Manager tree. The plane you select can't be at the exact location of a profile you're already using. It also has to be in an orientation where adding a loft profile would make sense. For instance, selecting the top plane in this example would not work. When you're happy with the position of the new loft profile, click OK. If you decide to remove the added loft profile, edit the loft and remove the profile from the list. The profile will become an unused sketch that you can delete if you wish. Like other standard features such as extrude, revolve, and sweep, the loft feature can be used to add material, but it can also be used to remove material. Take a look at this part. I will be using a cut loft to create a complex cut that connects these sketches. You can access the feature by using the Cut Loft icon found on the Features toolbar or from the Insert Cut drop-down menu. The Cut Loft Property Manager is just like the regular Loft Property Manager. I'll select the 3 profiles I wish to use and click OK. This is a good example of the complexity you can achieve by using the Loft feature. The Boundary Boss Base feature in SolidWorks is a great tool for creating complex 3D geometry. Like it says in the name, it's created by using curves to define the boundaries of the feature. The boundaries can be defined in 2 different ways, which I'll show you here in a moment. The Boundary Boss tool may seem a bit similar to the Sweep or Loft features, so it can often be confusing to decide which feature should be used. I'll go through some of the differences, and you can get a better idea of when the Boundary Boss feature is more suitable. For this sketch here, I'll first try using a Sweep feature. I'll start the Sweep feature and select the profile and path. And you can see that I can only create the sweep in a single direction. I'll instead start the Boundary Boss Base feature. For direction 1, I'll select the closed profile, and I'll add the second curve to the direction 2 box. This time, the solid body is created along the whole path, and I can even drag the endpoints to control the feature length. I can also define tangency types for the curves. And I can show zebra stripes or curvature combs to help visualize the surfaces. Even though the sweep and boundary seem to give you similar results in this example, it's important to note the differences. Because the Boundary Boss uses the second curve as a boundary rather than a path, the feature goes along the whole curve, regardless of direction. If I edit the path and create some sharper turns, and then create the Boundary Boss again, you can see the feature updates, and you get results that are a little different than you might expect. Certainly quite different than you'd get with the Sweep feature. I'll create a sweep instead. You can see that the part is created as you'd expect in the one direction. If I go under Options and get the orientation to keep normal constant, you can see it now looks pretty similar to the Boundary Boss, and in fact is how the Boundary Boss is calculated. So as you can see, while the 2 features can often give you the possibility of similar results, in certain situations, you'll get more control with one feature or the other. Next, let me show you the second way to define a Boundary Boss. I'll start the Boundary Boss feature and select both of these curves for direction 1. This looks pretty similar to a loft, and in fact will often give you the same results as a loft. But again, there are some subtle differences. The Loft feature is created between 2 separate curves, and a guide curve can be used to influence the transition. In a boundary feature, as we saw just a moment ago, the direction 2 curve acts as a boundary to the feature and is given the same weight as the direction 1 curves. As a result, boundary features give you different control over the transition between the curves and also more control over the curvature at the edges. For example, I have the ability to drag this point anywhere on the rectangle to change the curvature however I want, but with a loft, I am only able to move the curvature point to the vertices. If you're just making basic shapes, you probably won't notice much difference between lofts and boundary features. But if you need to create more complex shapes,
One feature over another may create nicer surfaces in addition to the increased control over transition and edge curvatures. Because of this, I would recommend experimenting with the different features, and over time, you'll be able to quickly decide which feature will be the most appropriate for the design you're working on. Just like with other standard sketched features, the Boundary Boss base feature has a matching feature that is used to remove material, the Boundary Cut feature. I want to create a cut through these curves, so I'll start the Boundary Cut feature from either the Features toolbar or by going to Insert, Cut, and Boundary. The Property Manager is the same as the Boundary Boss base Property Manager, so I'll select the curves here for Direction 1. I can also adjust the curvature and end conditions to make sure I get the cut that I want. When I click OK, the cut is created. Just like with the Boundary Boss base feature, the Boundary Cut feature will generally give you pretty similar results to the Swept Cut and Lofted Cut features, and it's up to you to determine which feature is the most appropriate for the design you're trying to create. In SolidWorks, the Dome feature is often used to create a spherical feature to round off a face in your model. The Dome feature can come in handy when you're modeling hemispheres or adding finishing touches to a surface of a model. Here I have a bottle, and I would like to apply a dome to the bottom face. To launch the Dome feature, I'll click the Dome icon on the Features toolbar. First, I'll select this bottom face to dome. Then, I'll set the distance to 0.5 inches. Notice that the dome is protruding outwards, which is not what I want for this part. So I'll change the direction by clicking Reverse Direction. The elliptical dome option forms the shape of a half ellipsoid, with the set height equal to one of the ellipsoid radii. This option is only available for cylindrical or conical models. I'll click the green check to exit out of the Property Manager, and the Dome feature has been added. Let me edit the feature to show you a few more options. The Constraint Point or Sketch selection box allows you to select a sketch to constrain the shape of the dome. Constraint sketches are generally circles or points, but you can use different shapes depending on the shape you want to get. I'll have to first roll back the model up before the Dome feature. I'll create a reference plane and offset it from the top plane by 0.5 inches. Then, I'll sketch a point coincident to the origin on the reference plane I just created. Next, I'll enable the Constraint Point or Sketch selection box and select the sketch point. When I have a sketch selected for this option, the distance and elliptical dome options are disabled, since the dome is already fully defined by the sketch. When I exit out of the Property Manager, you can see the updated results. The Wrap feature is used for wrapping a sketch onto a planar or non-planar face. It's similar to the Projected Curve and Projection Split-Line curve. But Wrap also allows you to add or remove material with your sketch. In addition, you'll see slightly different results with the Wrap feature since it wraps the sketch onto the face rather than projecting it onto the face, which can occasionally cause some distortion. You can find the Wrap feature on the Features toolbar. Here I have a sketch that I created with the Sketched Text tool, and I'd like to wrap it onto the cylindrical face. I'll use the feature tree to make sure I select the whole sketch, and I'm taken to the Wrap Property Manager. Here I have three options for the wrap parameter. Emboss will add material and create an extrusion. I'll select the cylindrical face for the wrap face. Set a thickness, and I can also change the direction of the extrusion by adding a pull direction, but I'll click the green check, and you can see the Emboss feature. I'll go back and edit the wrap feature, and I can change the parameter to deboss instead. This gives me the same options as emboss, but instead remove material. I'll click the green check and you can see the deboss feature. I'll edit the wrap one more time, and this time I'll use the scribe option. The scribe neither adds nor removes material. The only additional setting here is reverse direction. As I mentioned earlier, the wrap feature gives you slightly different results from the projected sketches. To illustrate this, I'll create a projection split line using the same sketch. And you can see how the two methods vary.
The flex feature provides a free-form method of bending, stretching, tapering, and twisting parts in a way that would be very difficult using standard sketch-based features such as extrude, revolve, sweep, and loft. In the next few lessons, we'll examine each of the options available within the flex feature in detail. The flex feature can be applied to any solid body, whether it was designed in SolidWorks or imported from another CAD system. In this case, I'm working with an imported model. Notice there are no features listed in the Feature Manager tree other than a single imported body. The Flex feature icon is not found on the Features toolbar by default. You can add it to the toolbar or access it from the Insert, Features drop-down menu. When the Flex feature is launched, as with other features, a Property Manager will appear, allowing me to define the parameters of the feature. The first item to define is the solid body that I'll be applying the Flex feature to. When it's selected, a few things appear in the graphics window. 2 trim planes are shown, 2 axes, and a triad. Understanding the role of these items within the Flex feature is the key to being able to use this feature intelligently. First of all, let's talk about the trim planes. By default, they appear at the extreme ends of the solid body you selected. Any region of the solid body that lies between these planes will be affected by the Flex feature and potentially be deformed. This is important to know, especially if there are regions of your model that you do not want to change. The position of these planes can be adjusted by dragging the arrows in the graphics area. The planes can be rotated by clicking and dragging their edges. You can also use a distance value through the Property Manager. This distance is measured from the extreme end of the solid body. In other words, setting this distance to 0 places the trim plane at the end of the model. You can also position trim planes precisely by selecting a reference vertex. You do this by activating the selection window for the appropriate trim plane and selecting a point vertex in the graphics area. Before we actually deform this model, let's take a look at the role of the triad in this operation and also look at how to manipulate it. I'll return the trim planes to their default position to make it easier to see the triad. The triad provides a point of reference for the flex operation. It acts as a coordinate system that defines the center of the flex operation, the orientation of the trim planes, and the direction of the axes. There are several ways to manipulate the triad. The simplest is to simply drag it. You can drag the blue point to move the triad freely in 3D space. Or you can click and drag the individual arrows to move only along the direction of the arrow. If you click and drag a rotation ring, you'll rotate the triad about the ring you've selected. Notice as I do this that the orientation of the axes and trim planes rotates as well. Also, you have some options that can help you when rotating the triad. If I right-click on a ring, I can select Snap while dragging, which will snap the rotation angle at every 90 degrees. I'm also given the option of rotate 90 degrees and rotate 180 degrees, which will automatically rotate the triad for the selected value. If you wish to control the location and orientation of the triad more precisely, you can enter numerical values in the Property Manager.
Notice there's a selection window where you can specify a coordinate system to use as a reference.
If you leave this blank, the coordinates are in reference to the part's global coordinate system. The position of the triad is critical to the outcome of the Flex feature. There are some helpful shortcuts available that allow you to position the triad based on other items. First of all, if I right-click anywhere in the graphics window, I'll see the option to Reset Flex. This returns the trim planes and triad to their default positions. Now that you've learned how to manipulate the trim planes and the triad, I'll go ahead and show you how to define the two axes. First, you must know what each axis represents. The blue axis is the trim plane axis and always aligns the trim planes perpendicular to it. The red axis is called the bend axis, and this is the axis which the part will bend about. Note that both axes correspond to their colored arrow. So to define each axis, you must right-click on the corresponding arrow and select Align with Selection. This option allows me to line up the axis to an item I select. If I select a planar face, the direction will be normal to the face. If a line or edge is selected, the direction will be along the selected line or edge. If a point is selected, the direction will be along a line that connects the point to the part origin. You may have noticed that I can also choose to Move to Selection. This option will not only align, but move the triad to the item I select. If I right-click on the center of the triad itself, I get several more options. We are once again able to select Move to Selection and Align to. A word of advice when using these options: I find it easier to use the method we just discussed, right-clicking each arrow to define the axes separately. Center and Align to Principal causes the triad to be positioned at the centroid of the part and aligned to match the principal axes of the model. The last two options provide a convenient way of aligning the bend axis, the red one, to either of the trim planes. In a moment, we'll see why this can be very useful. Hopefully now you have a better understanding of the roles of each of the elements of the Flex feature. In the next lessons, we'll use the Flex feature to deform several parts so you can see the effects of the many options we discussed here. In this lesson, we'll take a look at how to use the Flex feature to bend this part. I'll begin by activating the Flex feature from the Insert Features drop-down menu. I'll select the solid body I wish to apply the Flex feature to and make sure the bending option is selected. When the Flex feature is launched, the triad will be aligned to the principal axes of the solid body and positioned at its centroid. I'll align the blue trim plane axis so I can define the region that I wish to deform. I'll right-click the blue arrow of the triad and select Align with Selection. I'll select the vertical face of the bracket to make the trim plane axis perpendicular to it. I'll slide the trim planes to isolate the area I wish to bend. Now, I'll orient the red bend axis so that the bending takes place in the orientation I want. At the moment, if I specify a bend angle of 15 degrees in the Property Manager, you can see the model will bend downward around the red axis. I would like to bend the model around the green axis. Unfortunately, I can't just tell SolidWorks to do this. I have to change the orientation of the red axis, which is always the bend axis. I'll right-click the red arrow of the triad and select Align with Selection, and choose the top flat face. This makes the red axis perpendicular to the flat face, and the model is now bending in the direction I wish. One more thing I'd like to address here is the fact that both ends of the model are moving as a result of the bend. I wish to keep the mounting plate side fixed. To do this, I have to position the triad exactly at trim plane 1. This is easily accomplished by right-clicking the center of the triad and selecting Move Triad to Plane 1. This is the result I was looking for, so I'll click OK and the Flex feature is complete. Notice a couple of edges have appeared here on these faces. This is because SolidWorks tries to use analytical faces such as planes and cylinders if possible. If I enable the Measure tool and select the inside curved face, you'll notice it has a radius. This tells me it is a cylindrical face. If you're more interested in having a continuous face without the edges, you can edit the Flex feature and turn off the Hard Edges option. This leads to smooth edges defined by splines rather than analytical geometry. The bend region is now smooth, but by turning hard edges off, some of the original faces may no longer be analytical. These cylindrical faces are in fact no longer cylindrical. If you use the Measure tool, you'll find they no longer have a radius or diameter defined. Twisting a model with the Flex feature is simple to do. Just keep in mind that the twisting will always occur around the blue trim plane axis. Let's begin the Flex feature. Select the Twist option and select the solid body we're going to twist. Next, I'll adjust the trim planes so only the center is affected by the twist. I'll type in 40 degrees for the twist angle in the Property Manager. As before, when we look at bending, you can adjust the trim planes and the position of the triad to further control the way the model is deformed. In this case, I'll just click OK to complete the Flex feature. The Flex feature allows you to bend, twist, taper, or stretch a model. However, you can only do one of these at a time. If you wish to perform two or more of Flex features, you have to apply them individually. In this lesson, we'll modify this part by applying both tapering and stretching. I'll begin by launching the Flex feature. Selecting the body I wish to deform and choosing the tapering option in the Property Manager. Tapering is defined using taper factor in the Property Manager. A positive taper factor will cause the part to get larger along the direction of the blue axis, while a negative value will cause the part to get smaller. For this example, I'll type in 0.2 and click Enter to update the preview. I'm also going to adjust trim plane 1 so it lies above the horizontal connector. To do this, I'll activate the reference entity field for plane 1 in the Property Manager and select this point. I also want to move trim plane 2 so it lies below the upper holes. I'll do this by manually dragging the plane downward. Finally, to ensure that the lower part of the model doesn't change, I'll right-click the triad and select Move to Plane. I'll click OK, and the Flex feature is complete. That takes care of the tapering. Now I'll use the Flex feature a second time to include stretching. I'll launch the Flex feature. Select the solid body and choose the stretching option in the Property Manager. The region I want to stretch is the horizontal connector. I only want to stretch the connector itself, so I'll use the reference entity selection windows of each plane and select the interior vertexes of the connector. Finally, I'll specify a stretch distance of 3 inches in the Property Manager and click OK to complete the Flex feature. The Indent feature allows you to change the shape of a solid body by using another solid body. The solid body that is changed is called the target body. The solid body that causes the change is called the tool body. Let's take a look at a basic example of how to use the Indent feature. Here I have a single part file. It contains 2 bodies, as you can see in the Bodies folder in the Feature Manager tree. To make the point clear, notice that if I edit the second Revolve feature, the Merge Result checkbox is not selected. This results in two solid bodies, which is important. Otherwise, I cannot use the Indent feature. The Indent feature icon does not appear on the Features toolbar by default. You can add the icon or access the feature using the Insert Features drop-down menu. The Indent feature property manager appears. The first item I will select is the target body. This is the solid body that will be changed by the Indent feature. In this example, the orange body will be the target. I'll leave the Keep Selections option selected and move on to the next selection window labeled Tool Body Region. When selecting the Tool Body region, I'm actually identifying two things. I'm telling SolidWorks which body to use as the tool, but I'm also defining which side of the tool to use. For now, I'll select the top face of the tool body, and later we'll return to the selection window and examine this issue further. Here at the bottom, I'll specify the thickness of the Indent feature geometry and any clearance I wish to add. By clicking the reverse direction button, I can specify whether the resulting geometry should be larger than the tool body or smaller. To get a better view of what just happened, I'll select the front plane and create a section view. Looking directly at the front view, you can clearly see the resulting geometry. The Indent feature created a pocket in the orange target body that wraps around the tool body. There's a clearance around the tool body as I specified in the Property Manager. There is only one problem here. I didn't want the pocket to be formed above the tool. I wanted it below the tool. Let's edit the Indent feature to correct this. Remember, I mentioned that when selecting the tool body region, we were actually defining two things. We specified the tool body to use, which is correct, and we also defined which side of the tool body to use, which I did wrong. Instead of selecting the tool body from the orange part, I should have made the selection from below. This tells SolidWorks to create the pocket around the lower portion of the tool. Once I've made this change, you can see the preview of the Indent feature update. This is the result I was looking for. Before clicking OK, let me explain another way of correcting this mistake. I'll deselect and reselect the tool body above the orange part to go back to the wrong bad result. Notice the Keep Selections option is selected. This tells SolidWorks to form the pocket around the region of the tool that I select. I can change this setting to remove selections, and now the opposite will be true. This region I select will be removed, which is why the preview is now correct. The Indent feature cannot be patterned. If you wish to replicate the shape resulting from the Indent feature, you must first replicate the tool body used to create it. In this example, I have 19 solid bodies. The green body is one, along with 18 others. I'll use the Indent feature to create pockets in the green body that are formed around each of the other bodies. I'll launch the Indent feature. And before making any selections, I want to warn you, the Indent feature can be quite slow. With each tool body you select, a preview will be shown. With this many tool bodies, you want to avoid waiting for each and every preview. This is my suggestion. First, activate the tool body region selection window and pick each face along the bottom side of the green body. Once each tool body is selected, type in the parameters you'll be using. Finally, as a last step, select the green target body. It will still take a moment for the previews to generate, but it's not as frustrating as having to wait for each one separately. Once the preview shows up, you can click OK and the Indent feature is complete. To make sure you have the result you were looking for, you can hide the tool bodies. To do this quickly, open the Solid Bodies folder and Shift-select every body except Indent 1. Now right-click any of the selected bodies and choose Hide Bodies. There you have the final result. There are times when the target body and tool body intersect in a way that multiple tool body regions are created. Here, for instance, because of the ribs on the underside of the blue body, there are several distinct regions of the tool body. When I apply the Indent feature, I can have the option of selecting these regions or omitting them in the feature. Let's take a look. Now keep in mind that the Indent feature only works when at least two different bodies are available as they are here. I'll launch the Indent feature and select the target body. Next, I'll click on some of the tool body regions. I'm purposely not selecting all of them so we can take a look at the results. I'll click OK, and you can see that only those faces I selected are maintained. If you have a situation like this, and your intent is to keep all of the tool body regions, I suggest the following procedure. Let me click Undo to get rid of the previous Indent feature. When you launch the Indent feature, select the target body as usual. Activate the Remove Selections option. Instead of selecting the regions from the bottom, select the tool body from above. This tells SolidWorks you wish to remove the region you selected. I'll click OK to complete the feature, and I'll hide the tool body. You can see that a pocket was created for every tool body region. The Indent feature can be used with solid bodies or a combination of solid and surface bodies. The only combination not allowed with the Indent feature is surface-surface. That is, when both the target and tool bodies are surfaces. You have to have at least one solid body involved. In this example, I have a surface body and a solid body. I'll be using the surface to cut away material from the solid. Let's launch the Indent feature and select the solid as the target body. I'm only interested in cutting material away, so I'll check the Cut option and notice the Remove and Keep selections options go away. When the surface is selected, I have the options of changing the side of the solid body that will be cut away. If necessary, I can also add a clearance so that the cut is slightly offset from the surface. I'll click OK, and the cut is complete. SolidWorks allows the use of multiple bodies when designing parts. This opens the door to several design techniques that would otherwise not be possible. In the following lessons, we'll examine some of these techniques. First, though, let's take a look at what we mean when we talk about multi-body parts. Many people understand the term multi-body to be the same as disjoint body. However, take a look at this part. Clearly, there are only two disjoint or individual bodies, but in fact, if you look at the Solid Bodies folder in the Feature Manager tree, the part actually contains three solid bodies. The Solid Bodies folder serves as a container for the individual bodies that make up the part. From here, you can make selections of bodies for a variety of purposes, including changing their color, combining them, deleting them, hiding them, and so on. By clicking on each of the bodies in the folder, you can see the lower disjoint body is actually made up of two bodies. The bodies are touching, and although you can see an edge where they meet, there is no space between them. They form a continuous solid. However, because of the way they were created, SolidWorks understands them to be individual bodies. So why would you design a part this way? To answer that question, I'll right-click the Solid Bodies folder and select Show Feature History. This changes the display of the solid bodies to include an indented list of the individual features that make up each body. You can see the first body is made with a single extrusion, as is the second body. The third body, however, is made up of two features, an extrusion and a shell. Notice the shell only applies to the third body. To make this more clear, I'll delete the shell feature and recreate it. If I were to select this face on the upper body, the result would be a thin-walled block. However, if I create a second shell feature and select this face, the feature applies only to a single body. A local operation like this shell feature is one technique made possible through the use of multiple bodies. Other techniques include bridging, booleans, tool bodies, and weldments. We'll examine each of these in later lessons. Now let's turn our attention to creating multiple bodies, something we have to do before we can use any of the techniques I just mentioned. The number of bodies in a part can change throughout the design process. SolidWorks makes it easy to create bodies, separate single bodies into multiple bodies, and combine multiple bodies into single bodies. In this lesson, we'll take a look at some of the methods used to create multiple bodies in a part. The simplest example of how to create a multi-body part is to create a feature, such as an extrusion, that results in 2 or more disjoint bodies. This is easily done by creating a sketch with separate contours. When the extrusion is complete, 3 individual bodies are listed in the Solid Bodies folder in the Feature Manager tree. Note that although I used a single extrude feature in this case, I could easily have created these bodies using 3 separate extrusions. As we discussed in the previous lesson, multiple bodies do not have to be disjoint. For instance, if I create an extrusion on the face of one of these bodies, by clearing the Merge Bodies option in the Property Manager, the result is a separate body. You can see this in the Solid Bodies folder. Multiple bodies can also be the result of cutting a single body part. An example of this would be creating a cut that separates a body in 2. When you do this, SolidWorks will prompt you to select which bodies to keep. I'll select all bodies, and you can see the total number of bodies shown in the Solid Bodies folder is now 5. One other method of generating multiple bodies within a part is to use the Split feature. This method and its options will be covered in the next lesson. The Split feature can be used to separate single bodies into multiple bodies. It can also be used to automate the creation of an assembly after a body has been split. Let's see how this is done using this simple model. As you can tell in the Feature Manager tree, this part is made of a single body. From the Insert menu, I'll select Features, then Split. This opens the Split Property Manager. In the first selection window, I'm prompted to select Trim Tools. These will define how this body will be broken apart into multiple bodies. Trim tools can be reference planes, surfaces, faces, or sketches. I wish to separate this body into 3 individual bodies: the tab shape, the block, and a cylinder cut out of the corner of the block. The trim tools I'll use are this face where the tab and block meet, and the circular sketch. Next, I'll click the Cut Part button in the Property Manager. A couple of things change. Notice as I hover the pointer over the model, only some of the model is highlighted. This is a preview of the bodies that will result based on the trim tools I've specified. The bodies resulting from this operation can be kept or consumed. This is specified at the bottom of the Property Manager. When the Consumed option is selected, the selected bodies are removed from the part. To begin, I'll select all 3 bodies in the Graphics area, which will check the associated body listed in the Property Manager. I'll click OK to complete the split. As you can see, the geometry and the graphics did not change. However, if you look at the Solid Bodies folder in the feature tree, you can see 3 separate bodies are now recognized. Let's edit the Split feature once again and select Consume Bodies. Now when I click OK, the result is quite different. The geometry is gone, as is the Solid Bodies folder. By using the Consume Bodies option, I've instructed SolidWorks to delete the bodies I selected in the Split feature. Of course, when using the Consume Bodies option, you probably don't want to have all of the bodies selected. If you do, you'll end up with nothing, as I did here. The Consume Bodies option can be useful though. I'll edit the split once again, and this time I'll leave only the tab body and the cylindrical body selected. When I click OK, these are consumed, or deleted, and I'm left with this shape. In addition to being able to split and consume bodies, the Split feature also offers the option to generate an assembly from the resulting bodies. This time, I'll delete the Split feature and begin a new one from scratch. The trim tools will be the same: the flat face where the tab and block meet and the circular sketch. After cutting the part, I'll select all three bodies using the Show Bodies option. Next, instead of clicking OK to complete the feature, I'll click one of the labels shown in the graphics area. A window appears prompting me to give this body a new name. What I'm doing here is giving each body a part name. This will result in each body being converted into its own part file. I can repeat this process for each body, or to automate the process of naming each body, I can also click on the Auto Assign Names button at the bottom of the Property Manager, which will give each body a default name. Before clicking OK, notice a new selection window appears at the bottom of the Property Manager, prompting me to select an origin. This gives you the option of specifying an origin for each of the part files about to be created. I'll leave this blank. When you do so, the origin of this original part will be the same one used in the resulting parts. I'll click OK. You can see three bodies are now listed in the Solid Bodies folder. By using the File, Open menu, you can also see that each of the bodies I defined have been saved into their own part files. I'll open the block body part, and you can see the result is a derived part. A part file that, instead of having a complete feature history, contains only a single feature with a reference back to the original multi-body part file. In this way, any changes made to the original part file are reflected here in the derived part. One more option remains. Since several bodies now exist in the original part file, and since each body has been saved into its own part file, you can now automate the creation of an assembly. The resulting assembly will be an exact replica of the original multi-body part, except it will be made up of individual parts rather than bodies. To create this assembly, go to Insert, Features, Create Assembly. The Create Assembly Property Manager will prompt you for two items. You must select the split feature you've already created. It will identify the part files that resulted from the split feature. You also have to provide a name for the assembly file about to be created. Once a name is given, click OK and an assembly file appears. The resulting geometry is identical to the original multi-body part, but now each body is a separate part file. This means, among other things, you can now run interference detection, create a bill of materials, and do other things that aren't possible within the part environment. One more word on creating assemblies from multi-body parts. In this example, I first used the split feature to generate individual part files, then used the Create Assembly feature to generate an assembly. If you have a part with multiple bodies that resulted from using the split feature or any other method that can result in multiple bodies, you'll use a different feature to generate your assembly. Here I have a part with multiple bodies. To create an assembly from this part, I'll use Insert, Features, Save Bodies. This brings up the Save Bodies Property Manager. Notice each body is already listed in the resulting parts window. By selecting the checkboxes next to each body, SolidWorks will assign a default part name to it. To overwrite the default name, double-click on the file name in the list. Next, I'll click the Browse button in the Create Assembly section. By providing an assembly name, SolidWorks will not only generate the individual part files from each solid body, it will also create the assembly. The result is 4 new files, 3 part files and the assembly file, each referencing the original multi-body part. Now that we've seen how multi-body parts can be created, let's take a look at some examples of why you might consider designing with multi-bodies. The first technique we'll discuss is bridging. Bridging is a technique where 2 or more disjoint bodies are connected by another body. This technique is useful when you wish to use 2 known bodies as the basis for defining a third body. Let's use this wheel as an example. I'll roll back to the point just after the 2 revolve bosses. Here I've defined the geometry of the hub and the geometry of the wheel. These 2 elements are the most important in this design. They must meet specific standards. The geometry that will connect them is not guided by standards, but rather it will be a freeform shape. By having the hub and wheel in place, I can now use several methods to design the spokes. In this example, I've defined 2 shapes using split lines on the existing bodies. Next, I've created a loft connecting the 2 shapes using a centerline. The last step is to add fillets to blend the transition between the bodies. Next, let's take a look at the use of multiple bodies to create local operations. This ratchet model is currently a single solid body. What I'd like to do is hollow out the head of the ratchet to make room for the ratchet mechanism. Using the shell feature would be an ideal way to accomplish what I want. Unfortunately, because of the way the model was created, using the shell feature at this point would present a problem. Take a look at what happens when a shell with a thickness of 0.2 is applied, removing the top face of the head. To make the problem obvious, let's take a look at a cross-section of the part. The entire model has been shelled. This type of problem can be avoided by taking advantage of multiple bodies. First, I'll turn off the section view and delete the shell feature. Next, to split the head portion into a separate body, I'll use the split feature. As we saw in the previous lesson, all I have to do is define the trim tool. Cut the part, select the solid bodies. This results in two bodies, as you can see in the Solid Bodies folder. Now I can reapply the shell feature using the same top face and 0.2 thickness. This time, however, the shell is only applied to the head portion. This is what we mean by a local operation, an operation limited to a single body, made possible through the use of multiple bodies. Before moving on to some of the other multi-body techniques, let me point out a small problem. Suppose now I want to add fillets to this model. Specifically, I want to break the hard edges between the head and the handle. Using the fillet feature, I'll select the edges around this area. When I click OK, I'm left with an interesting result. We'll examine this problem in the next lesson. In the previous lesson, we saw how adding this final fillet feature to the edges where the head meets the handle led to strange results. The results are easier to see if the solid body making up the head is hidden. Now you can see what's happened. Since this model is made up of two solid bodies, the edges I selected when I created this fillet are not edges where the two bodies merge. Rather, they're edges that belong only to the handle portion. When I added the fillets, it's as if the head didn't exist. Just like there can be advantages to having multiple bodies, such as the results of the shell feature we saw in the previous lesson, there are also disadvantages. Fillets and other applied features such as draft, chamfer, and shell can only be applied to one solid body at a time. Because of this, if you wish to create a fillet across multiple bodies, as I want to do here, you first have to combine the bodies into a single body. To do this, you'll use the Combine feature. You'll find the Combine feature in the Insert Features drop-down menu. You'll see in the Property Manager that the feature actually provides three types of Boolean operations: add, subtract, and common. In this case, I'll be using the Add option to add two of the bodies together. When I click OK, you can see only one body is listed in the Solid Bodies folder. Of course, the fillet problem is not resolved yet. The Combine feature, like any other, is time-dependent. That is, it matters where along the feature tree it's added. What I should have done is use the rollback bar to just before the fillet and executed the Combine feature there. Or I can just as easily drag and drop the fillet to appear after the Combine feature. When I do this, the fillet changes to show the result I expected. Now that we've seen the Combine feature, let's talk about the other multi-body design techniques it offers. Here I have a part made up of two bodies. By using the Combine feature's Common option, you can generate bodies defined by the intersecting volume of two bodies. When I click OK, you can see the result is a single solid body. The last Boolean operation offered by the Combine feature is subtract. As you can imagine, this performs the function of subtracting one solid body from another. Here I have a part made up of two bodies, one plate and a tube that runs through the plate. What I'd like to do is remove the volume of the tube from the plate. The plate can then be cut in half so that when the halves are joined together, a channel is formed through which liquid can pass. I'll again use the Combine feature, this time selecting the Subtract option. The main body will be the portion I wish to keep. In this case, that will be the plate. The body I wish to remove is the tube. I'll click OK. Notice the tube body is now gone. It's consumed in the process of creating the combined feature. A single solid body remains, and when I switch to a wireframe view, you can see the cavity left by the tube. To complete the design, all I have to do is separate the plate in half. One way to do this is to use the split feature. I'll begin by sketching a line that divides an end face in half. I'll exit the sketch and launch the split feature. The trimming tool will be the sketched line. I'll click Cut Part, select both bodies. When I click OK, I'm left with two bodies as I expected. If necessary, I can now use the Save Bodies feature to generate two individual part files and an assembly as we saw in the earlier lesson on the split feature. When working with multi-body parts, there's a powerful tool that you can use to create and modify geometry. It's called the Intersect tool. The Intersect tool is really neat and has quite a few capabilities. I won't be able to show you them all here, but I'd like to show you a few ways to use it to get you started. The Intersect tool lets you intersect solids, planes, and surfaces to modify existing geometry or create new geometry. For example, you can intersect a surface with a solid to add detail to a face or remove material. You can create geometry from an enclosed cavity. For instance, if you have a mold, you can see the output part from the cavity. There are lots of other uses as well, like merging solids or capping surfaces to close a volume. Let me show you a couple quick examples. In this part, I have a surface body and a solid body. I'll launch the Intersect tool from the Insert, Features drop-down menu. I'll select the two bodies and click Intersect. When I do, the Regions to Exclude list populates, and I can choose which regions I'd like to keep or get rid of. You can use the Invert Selection button to update your preview and flip your selections. At the bottom, you have the options to merge result, which functions just like it does everywhere else in SolidWorks, and the ability to consume surfaces. If you check this box, the surfaces will be absorbed by the Intersect feature, which you may want, or you can keep it cleared to keep the surfaces. When I click the green check, you can see the results. Pretty easy, right? Even though it's easy to use, if you use it creatively, you can create some really complex geometry that would have required many more features in the past. Let me walk through one more example. Here I have a multi-body where the bodies are overlapping. I'd like to use the Intersect tool to create a solid from the overlapping region, similar to what you'd get with a combined common feature. I'll launch the Intersect tool and select the two bodies. Next, I'll click Intersect and the Regions to Exclude updates. In the Regions to Exclude, I can see the three regions here, the two original bodies and their intersection. I'll choose to remove the two original bodies and click the green check, and you can see the resulting part. In a previous lesson, we discussed swept cuts. But be aware that if using sweeps, you also have the ability to use a solid body as a cutting tool. There are just a couple of rules that you have to keep in mind. Here on this part, I'm going to use the red geometry as my tool body to sweep a cut along the path sketch that I've already created. The red body was created using a revolve feature, which is the first rule. The tool body must always be a revolve feature. Second, when it was created, the merge result checkbox must be unchecked, resulting in the two separate bodies. Finally, the path sketch that we'll be using here intersects with the tool body, and all of the segments have sketch fillets that create tangency around the path. To launch the Swept Cut feature, I can select the icon from the Features toolbar. To use the solid body as our cutting tool, I'll enable the Solid Sweep option. The procedure here is almost identical to a regular sweep. If I hover my cursor over the first input window, you can see that SolidWorks is prompting me to select the tool body. I'll select the red tool body And when I do, the other selection window becomes active where I can select the path sketch. When I select it, the entire path will highlight. I'll click OK, and the feature is created. Notice the tool body is no longer visible, and if you look in the Solid Bodies folder, only the main body is shown. This is because the swept cut feature consumed the tooling body after the cut. Let's go through one more quick example. Here I have an extruded cylinder, and again, another revolved tool body that I can use for the cut. The path sketch I'll be using here is a helix. I'll again launch the swept cut tool, enable the solid sweep option. I'll select the revolved tool body, and the helix is our path. I'll click OK, and the solid swept cut is created. In this lesson, we'll examine tool body and symmetry, two other techniques that take advantage of multiple bodies. Tool body simply refers to the idea of incorporating an external body into the design of your part. It might be a specialized, commonly used feature that can be easily replicated by adding or subtracting geometry from your part. Take this part for instance. Suppose this geometry represents a set of cuts that are commonly used in my designs. Of course, here you're seeing the negative space of the feature, where material is to be removed. Rather than create these cuts each time I need them, I simply design this part as a tool that I can apply to any other part. This is how it's done. I'll begin with a plate, the only feature in a new part file. The cut pattern needs to be replicated a total of 4 times along an edge of this plate. To begin, I'll introduce the tool body by using the Insert Part command. I'll browse for the tool body and click Open. In the Property Manager, I can specify what information I wish to bring in from the tool body in addition to its solid geometry. To continue, I'll use the Move Copy feature. I'll slide the tool body into the lower left corner. Next, I'll use a linear pattern to replicate the tool body a total of 4 times along the lower edge. Finally, I'll use the Combine feature to subtract the tool bodies from the plate. The result is what appears to be a pattern of cuts. The tool bodies are consumed during the Combine feature. Also, since I have an external reference to the original tool body, if I were to make changes to the tool body part, these cuts would update to reflect those changes. Although for this example, I was not concerned about the exact position of the tool body. To effectively use this technique, you will want precise control over its position. In the next lesson, we'll take a look at positioning bodies using mates. To conclude this section on multi-body techniques, I'll discuss the use of symmetry. The concept is not new. You use symmetry to speed up your designs all the time. If you notice the need for a symmetric sketch, you create half of it and use the mirror tool to generate the rest. If you have a feature that repeats in a circular arrangement, you use a circular pattern to save time. These same ideas often used with sketches and features can also be applied to solid bodies. You actually saw an example of this just a few moments ago when I created a linear pattern of the tool body. To complete this design, I'll simply use a mirror feature to create the other half of this plate. The mirror face will be this one here. Instead of selecting a feature to be mirrored, I'll expand the body section and select the entire body. I'll click OK, and the mirror is complete. Earlier we saw how the Move Copy feature can be used to position bodies within a multi-body part. You can also use mates to control positioning more precisely. Before we continue, it's important that you not mistake this functionality as a substitute for assembling components in the assembly environment. We'll take a look at the differences a bit later. Let's take a look at how mates are used using this multi-body part. I'll add a plate to be attached at the base of each leg. I'll add the plate using the Insert Part command. Before I add the part, notice the Launch Move dialog option is checked. When I click in the Graphics area to drop the part in, the Locate Part Property Manager appears. As you can see, this looks very much like the Mate Property Manager you see in assemblies. You select Entities to mate, then select the appropriate type of mate. In this case, I'll make the top face of the plate coincident to the bottom face of the leg. To apply the mate, you simply click the Add button. Next, I'll add a couple of distance mates to position the plate under the leg. I'll click OK, and the plate is in place. Earlier, I mentioned this new functionality should not be confused with the use of mates in the assembly environment. One reason is that here in the part environment, I cannot make use of the Move Component tool. This keeps me from simulating motion, using collision detection or clearance detection. Also, since I'm not working with an assembly, a bill of materials cannot be automatically generated. The main difference between using mates here in the part environment versus using them in an assembly is that here they're used only to position bodies in a time-dependent fashion. I'll show you what I mean. After positioning this plate as you just saw, I can launch the Move Copy feature, select the plate as the body to move, select the top face of the plate and the top face of the weldment to create a coincident mate. After doing that, I can use the Move Copy feature again to move the plate somewhere else. This behavior is completely different than what you would expect in the assembly environment. Here, as long as I use the Move Copy feature again and again, I can create mates that would seemingly conflict with earlier mates. If you look at the Feature Manager tree, you'll see the mates I just added are associated with individual Move Copy features. Like any other feature, these can be reordered, suppressed, deleted, or you can roll back to before they were created. The point is, these mates do not behave like mates in an assembly. They only apply until you add another Move Copy feature that moves the body again.
Most SolidWorks users are familiar with creating exploded views to help document and visualize their assemblies. SolidWorks also allows you to explode multi-body parts in much the same way. Showing parts in an exploded state is a great way to see how things fit together and to communicate assembly order and instructions, among other things. Here, I have a simple multi-body welded frame that I'd like to show in an exploded state. To create the exploded view, I'll go to Insert, Exploded View. Or I can switch to the Configurations tab, right-click on the default configuration and click New Exploded View. The process should hopefully look familiar to you if you've used exploded views with assemblies in the past. I'll click on the first body and a triad appears. Now, I can simply drag the component wherever I want using the triad. Or for a more precise distance, you could type it into the Property Manager. There are a couple other options you have that can help you better control where your components are located in the exploded state. One option you have is to align components to specific parts of the model. To do this, I'll right-click on the origin of the triad, select Align To, and align it to this face, and the triad will change to that alignment. You can also control the spacing between the components to automatically have them evenly spaced out. Under Options, check the Auto Space Solid Bodies after Drag checkbox. Notice when I drag the bodies out, a space is automatically added so that they are evenly spaced. Once everything looks the way you like, just click the green check and the exploded view configuration is created, and you can see it here in the configuration tree. I can switch back and forth between the collapsed and exploded states by double-clicking the exploded view in the configuration tree. To make any changes, I can just right-click the exploded view and select Edit Feature. I can add steps like before, or I can right-click a step and either delete it or edit it. If I click Edit Feature, I can use this arrow to adjust its position and the direction I chose earlier. I'll click the green check again, and notice that if I expand the view, I can also right-click any of the explode steps or again delete and edit it. Just about all of the options you have with assembly exploded views are available to you in a multi-body part, but there's still one limitation. You can't animate the exploded view in a multi-body part like you can for assemblies. One other thing to be aware of here is that when your part is in an exploded state, you cannot add any additional sketches or features. All of your toolbars will be grayed out until you return the multi-body part to its collapsed state. However, you can add an exploded line sketch to annotate your exploded view. To do this, I'll go to the Insert drop-down menu and select Exploded Line Sketch. All I have to do is select the components I want to connect with the line sketch, and SolidWorks automatically connects them with a 3D sketch line. I have three options at the bottom. I can select a part in the Items to Connect selection box, and click the reverse checkbox to switch the side that the line passes through. I can also click the arrows in the graphics area. I can also alternate the path and choose if I want the line to always follow the X, Y, or Z axis. Once the line looks the way you want, click the green check and it's added. Notice the Property Manager stays open so you can create additional lines without having to restart the tool. When you're done, just cancel out of the Property Manager.